So my name is Tom Fitzpatrick. I'm a verification evangelist at MITRE Graphics. That's the coolest title I've ever had, so I like to tell people about it. So I'm going to start off today, and we have representatives from several other companies that are going to be speaking to you throughout the day. So welcome to UVM Ready, Set, Deploy. So the agenda, we're going to go through some of the concepts of UVM in the morning. Then at lunch we'll have a town hall meeting with our friends from NASCUG. And then in the afternoon we have a number of user companies that are currently using UVM and are going to share their experiences as well. I am going to talk about base classes in the UVM, sort of the basic concepts, give you a kind of the lay of the land of UVM. What we're going to do, we're going to try to give you a real good foundation for the concepts. There is going to be some code on the slides. If you're not familiar with the syntax or what have you, don't worry too much about it. A lot of these things, as you'll see, are going to turn out to be idioms that you sort of have to know what they are and just type them and not worry about why you're typing what you're typing. Just know that this is what you have to type. So the whole idea behind UVM is we got together and decided that it really would be a good thing if everybody did the right thing. Right? Wouldn't that be nice? What we really came to the conclusion was that, you know, System Verilog itself is a fairly big thing, and I know because I've been working on it for a long time. When it comes to verification, what you really want to be able to do is take System Verilog and use the pieces of System Verilog that make sense for verification to do verification in a way that makes sense. Right? So what we're really talking about doing is making sure that everybody uses the same things in the same ways. Right? So it's really about developing people and teams that can communicate with each other. So we want to develop a common skill set, a common language for referring to things. You don't want to have one person talking about an A and somebody else talking about a B when they're really both sort of doing the same thing. We want to say, okay, this is an agent or whatever we want to call it. Right? We want to have a common strategy, and we want everything to be clear and transparent so that if you, for some reason, maybe go to a new company or hire somebody new, you can immediately come up to speed and talk in the same language and become productive and work together. Right? So what we're really doing here is providing you freedom from choice. Right? The biggest problem with reuse is everybody does something different and nobody can reuse what anybody else is doing. So we want to have a single framework, a single structure for how to do stuff. So therefore we avoid chaos, we avoid repetition, right? We don't want to always have to reinvent the wheel. And what we really are trying to do here is to come up with a set of APIs so that everybody knows, okay, in order to generate stimulus, I need to do this. In order to see what's happening on the bus, I need to do that. Those kinds of things. Right? And the idea here is that it's not just for superheroes, right? There's always a few people that are going to do a lot of the infrastructure work that most of us mere mortals probably don't even want to deal with, but we all need to be able to use the stuff that they provide, right? So the key is to understand how things work, even if you can't necessarily create it from scratch yourself. But once you get handed a piece of IP, you recognize it as this is a piece of UVM IP, this is something I know how to deal with, I know how to generate stimulus with it, I know how to do functional coverage with it, or whatever, right? So that's really what we're trying to get to. All right, so again, we're not reinventing the wheel. The key here is reuse, right? So we want modularity, we want flexibility, and we want portability. So the idea is to take this thing called System Verilog, and what we really want to do is create our own VIP and our own environments. So UVM is this class library and a methodology that bridges that gap. All right, so this is what you should keep in mind. What we're really focusing on is taking all of this stuff and providing you a means for creating your VIP and your verification environments. And those verification environments often involve VIP from other sources as well. So we want to be able to make sure everything works together. All right, so the key concepts that we have here, there is a distinction that we make between a test and a test bench. Right? So the test bench, also referred to as an environment, is the structure of stuff that you need in order to do your job. And the test is the set of stimulus and coverage and other things that, basically the tweaks that you're going to make to that test bench to exercise a specific piece of your test plan, right? When we build the environment, we do it in a phased process, right? So the first thing we do is we instantiate the components, and we're going to go through this in a lot more detail. We connect the components, and then we can configure things. All right, so the test really controls that configuration. There's probably going to be some default configuration in the environment, but the test's job is to really do that final tweaking of things. So it allows us to change structural parameters, such as how many things are on the bus. It allows us to change runtime parameters, how many wait states should be injected in the idle step or things like that. And it allows us greater topological flexibility. So you can actually write an environment that says something like, I can have from 1 to 10 things on the bus, and the test decides how many to do, right? So one test might have one thing on the bus, just do a pretty straightforward sanity check, and then you can randomize how many things are on the bus and things like that, right? So you have that flexibility. And it's really up to you, right? Your environment can be as flexible as you want to make it, right? You can easily write, you can write an environment that has 27 different parameters that define all the different things about how many things are going to be on the bus and how they're going to interact and all that kind of stuff. If you can keep track of that, great. You can have one environment with all those parameters on it, or you can have 27 different environments and pick one. Okay, so it's up to you how you want to organize that. As we'll see, the decision to make between those is really up to you, and it really doesn't matter, right? Ultimately, you're going to wind up with an environment that has the number of things on the bus that you want that are configured appropriately for your particular application, and off you go. Right. The thing that makes this all possible is the use of TLM, or transaction level modeling. We'll talk about this a little bit, but TLM basically started in System C, and it is a way of defining communication at the transaction level. Right? And a transaction, as we'll see, is whatever you need it to be. Right? Whatever piece of information you need to communicate from one component to another, that's a transaction. And the key to transaction level modeling is that we communicate between interfaces, not between components. So it's very easy to replace one component with another. Oops, I think my animation's a little screwy here. Right? You can replace one component with another that uses the same interfaces, and all the other code still stays the same, right? So the environment code that instantiated this component stays the same, but the test can now tell the environment to stick in a different type of component there in that slot, right? And that's where we get the flexibility, right? And then the other thing that we've created is this notion of hierarchical sequential stimulus, right? So the stimulus is defined independent of the rest of the stuff that's going on. Right? You define what your stimulus is going to be, and then one of the things the test decides is which of my stimulus generators is going to run this particular sequence. Right? So we decouple the stimulus from the component hierarchy. It becomes a very straightforward interface for the test writer. Test writer says, I want to run this sequence over here. I want to run that sequence over there. I want to put this piece of functional coverage in over here. Right? And that's pretty much it. By the way, feel free to ask questions at any time. All right, so when we build an environment, we have this phase we call build phase, right? So the whole thing in UVM is you call this thing called run test, and we'll get into that in a minute. And then from there, the UVM infrastructure goes through and calls the methods of every component in order, right? So the first thing that we call is called build phase. And what happens in build phase is we instantiate the components. So the test is going to instantiate the environment. And when we instantiate components, we don't actually call new on them in System Verilab. We don't construct them explicitly. We call what we call the factory, right? So the factory is a typical object-oriented programming pattern. People have been doing this for years. And what happens is the factory knows how to create an instance of the type of thing that you want and returns that instance. So the effect is as if you called new on it, but what happens is the factory has the flexibility so that you can decide, no, actually, instead of an A, I want a B. Right? And we'll go through that in a minute. Right? So build phase gets called hierarchically top-down. So the test instantiates the environment instantiates children, those children instantiate their children, etc. Right? And this allows us now, because we're using the factory, to override the type of a specific component. And you can override it by type or by instance. And then we have a phase called connect phase, which gets called automatically after build phase, and that actually does all of the connections for you. Right? So all these, right? So all the connections between ports and exports and your TLM interfaces, that happens at connect phase. So what that means is that all of your components are instantiated, and then you go back later and connect them. Right? So at the end of all of this, there is a method called end of elaboration phase, which is just a handy place for you to do whatever else you want to do. So at the end of elaboration phase, everything is completely built and connected, and you're stuck with it. Okay, you can't go back and change things. What you can do in end of elaboration phase is modify some initial settings of things, print out your topology if you want to see how your random build stuff turned out and things like that. So end of elaboration phase is a nice thing to do. But at the end of that, you're done. You're built. That's it. This is what you're running with. Right? So the key to all of this, though, as I said, right, it's all about reusability. The environment code doesn't change. So the test now can modify things through the factory and the configuration database, which Kathleen will talk about a little bit later. But this is what gives you the flexibility now. So because the environment is written in terms of understanding the fact that these things are generated from the factory and can be configured, then you have that flexibility to alter what happens in the environment without the environment code having to change, because the environment was written to accept those kinds of changes. Right? And the other thing to remember is, boy, the animation is not really working very well here, is it? Right? That environment itself as a component gets created from the factory. So as I said before, you can actually replace one environment with another in exactly the same way that the factory can replace one component with another. It's the environment gets created from the factory. So the test can actually choose a different environment to run with, the same way that it can tell the environment to instantiate a different component. Okay, so when it comes to putting together a test bench here, we need to think about what our DUT is going to do. And there are two orthogonal concerns here. The first is for each interface that we use to the DUT. How many of you have DUTs with interfaces? Okay, right. So for each interface, we want to think about how does that interface work, right? What information are we transferring to it? What are the variations of the transactions that are going to happen? Is it unidirectional, bidirectional? Is it pipelined? Right? We need to think about how are we going to communicate with this thing that is completely independent of what that device is actually going to do with that information. Okay? That's what the design is, right? So we need to think about what is this design supposed to do? Right? When somebody says, does your design work, can you say yes? Okay? What does it have to do? So what are the use cases? What test cases are required? What are the things I have in my test plan? How many of you have a test plan? Okay, that's a serious question. How many of you have a test plan? Okay, good. All right. So what type of stimulus scenarios do we need? What does it mean to represent correct behavior? How do we know that this thing is right? Right? And what kind of functional coverage do I need? Those are things that are specific to the design. So if I have this design that is meant to take something from here and put it over there, I can change the type of interfaces that I use, but it doesn't change the fact that this device is still supposed to take this from here and put it over there. All right? So these two concerns really are orthogonal, but we need to make sure that we exercise both of them. We want to make sure that in all of our communication with this device that we're going to exercise all of the different ways that the interface can be used. Because God forbid we don't test something and we give it to a customer and they plug it in and they try to use that interface in a way that we forgot to test. Right? So we don't want that to happen. All right. So the way that we interact with a device through an interface is with what we call an agent. All right? So there's typically one of these per interface, and inside of that agent you have several key things. And these are terms that everybody needs to understand so that when you go and talk to somebody else about UVM, you make sure you're talking the same language. So we have this thing we call a driver. And the driver's job is to communicate at the pin level with the DUT. Okay? The information that gets communicated comes from a sequencer, and the sequencer runs a sequence that generates sequence items, also known as transactions. So that sequence item goes to the driver takes that information and uses it to control the pin wiggles to the DUT. And that's how we interface with the DUT. Then we have a monitor that is connected to that same interface to the DUT, recognizes those pin wiggles as a transaction and communicates that transaction out through an analysis port to the rest of the system, whatever that means. I don't care who wants to know this, but somebody probably does, and I am up there and I am saying, okay, I saw this transaction, here it is. Okay. The key to all of this is that these things are configurable. All right, so a configuration object is, you can think of it kind of like a transaction. It includes in it whatever information is necessary to tell this agent what to do. Okay, and one of the most basic things about this agent is whether it's active or passive. Right, so an active agent actively drives stuff onto the bus. A passive agent does not, but the monitor is still there to report what happened. All right. Okay, so here's an example of the code that we use to instantiate the agent. I'm not going to go into a whole lot of detail here. I just want to show you it. So the agent instantiates the different components that are going to be there. You have the analysis port, the monitor, the driver, the sequencer. Right? The analysis port, by the way, is technically a component. It's something you need to deal with. And then in build phase, the first thing we do we call super build phase, so that if there's anything else that happened in the base class, we get that as well. And then we go to the configuration database, which Kathleen's going to talk a whole lot about. But basically you say, did anybody set configuration for this? And if the answer is yes, we're going to use it. If the answer is no, it's up to you whether that's a fatal, somebody really needed to tell me what to do and they didn't, or I'm going to pick some default or whatever, right? So you can issue messages as necessary. You can say, I'm going to use default and this is what I'm going to use or whatever. It's up to you. And then once we get that configuration, we say, okay, am I active? If I'm active, I'm going to instantiate my sequencer and my driver. If I'm not active, I don't even instantiate them, so I don't need to worry about connecting them. Right? And then I instantiate my monitor. Typically, I always instantiate my monitor. Right? And then in the connect phase, we go and connect things up. So we connect for the interface. Right? This is the interface here is actually, it's a virtual interface. That's the way classes connect to physical pins in System Verilog. So we assign that to the interface in the monitor. And then we connect the analysis port to the monitor's analysis port. And then if it's active, we go and we connect the sequencer and the driver. All right. And then if it's active, then we also have to connect the driver to that same virtual interface. All right. So again, this is a typical pattern of code that you're going to see. If you don't get it right off the bat, don't worry about it. You have you'll get access to the code and you can see it. Just sort of be aware. Basically, what we're doing is we have everything there. We instantiate it from the factory, and then if it's active, we put in the driver and the sequencer. And then at connect time, we go and connect the things that are definitely there. And then if it's active, we go and connect the driver and the sequencer. All right. And then in the environment, again, we may have multiple agents here, as well as probably a scoreboard, and there's probably other things here, but just to keep it simple. So in the environment, again, everything has a constructor. All the components have the same constructor. They have two arguments: the name, and you can give it a default. In this case, my environment, and the parent. By default, the parent for anything is null. Somebody was beeping. All right. Then in the build phase, what we do in the environment is we go and we look in the configuration database for something that's going to configure us, right? And the configuration database, as Kathleen will show you, is typed here. So we're looking for a my environment config thing in the config database, and if we get it, we're then going to use that. If we don't, it can be an error, fatal, whatever. Yeah, question? Okay, then in the connect phase, we go and we say, okay, what do I have? And if I have my scoreboard in there, then I have to go and connect it. Right? So I connect the analysis port of my agent 1 to my scoreboard, and then I connect the analysis port of my agent 2 to the scoreboard. And now I have my scoreboard up and running. Right? So again, it's up to you. Based on what you wind up instantiating in your environment, you need to make sure that everything gets connected. Right? And now you have your customizable environment customized to your particular application, and you can start running. right, so very quickly through the configuration database, the UVM config database is a convenience layer. Kathleen's going to go into a lot more detail here, but basically for every component you have a default value, and then that can get overridden by a parent, where the parent says, okay, I'm going to set the X value in my driver to be 2, so now the value that the driver gets is 2. The environment can set agent.driver.x to 3. The test can set environment.agent.driver.x to 4. So basically what happens is we look at where you are in the hierarchy, and the highest guy in the hierarchy wins. Right? Typically these kinds of things get set at build time, so build is top down, so it's really the first right wins if you want to think about it that way. But we actually do look at where you are in the hierarchy, highest right wins. But what we recommend doing is, rather than reaching all the way down from the test and going all the way down into the driver and setting X to be 4, what we do is we say, okay, from the test I'm going to set a parameter in my environment, and then my environment is going to get that parameter and use that information to set the value to the agent. The agent is going to get that value and use that to set the value in the driver. All right? This is much more reusable. In the test, by the time you get to end of elaboration, you know what you wound up instantiating in your environments and agents and everything, so you could theoretically, at that point, reach down all the way down and set a value to something, but we really don't recommend you doing that. What we really recommend is using the configuration database to pass these things down layer by layer. Right? All right, now when we get to stimulus, the whole key here, as we said before, is to separate that behavior that you're dealing with from the structure of your test bench. Right? We don't want somebody to have to write a sequence that depends on a given setup in your test bench, because that's not reusable. Right? You really want to write your sequence in terms of what information am I trying to communicate to my device. And so we use those, we do these through sequences. So in my sequencer, I'm going to execute a bunch of stuff that defines a transaction stream, right? And we call that a sequence. So I can have multiple sequences. They can run in parallel. Sequences can call children. So I can have, S5 can call S1. That might be my test setup stuff, configuring my device or whatever. S2 and S3 running in parallel could be the meat of my test, and then S4 could be some cleanup or what have you, right? So the idea here is sequences can call other sequences, and I think John's going to talk about what we call virtual sequences, where you have a sequence that controls the sequence execution on multiple other sequencers. Right? So it's all hierarchical in this way, and it allows you to have that flexibility. Sequences and the transactions they generate are also customizable by the factory. All right? So if you want your test to say, okay, even though I thought I was running a yellow S1, I actually want to run a gold S1. Right? You can do that. And it'll run a different sequence. As long as that sequence generates the same transaction types, you can do that. All right. Now, when it comes to designing a sequence item, as I said earlier, the sequence item contains whatever information is necessary for your application to communicate from one component to another. Okay, but there are certain things that sequence items have to do, because they're used by other things in the system that expect the sequence item to be able to do those things. So we define in it whatever it is we need. So we extend it from the UVM sequence item, that's the base class. The UVM object utils macro allows us to register it with the factory, and Kathleen will talk a little bit more about that. And then we define for it all of the all the information that it's going to contain. Now, there's usually what we refer to as input properties and output properties, right? Address and data are typically input properties of a transaction, right? When you create the transaction, you're going to say, I want to write to this address with this data. Those are input properties. We typically make those random, right? So when we randomize the sequence item, those are the things that are going to get randomized. There are other things that are output properties that we don't want to randomize. And then there are a number of methods that we need to define for every transaction. Right? And those are listed here: do copy, do compare, convert to string, do print, do record, do pack, and do unpack. Right? There's a lot of information about how to do these if you want, but the thing to remember is you're never going to call these directly. Right? In your code, you never call do underscore anything. right, unless you write it yourself. For these things, there is a method that you call that's called copy, compare, or whatever. Basically, remove the do underscore. That's what you call, and then the do method gets called by the UVM infrastructure at the appropriate time. All right. So let's just go through one quick example here. So we'll take a look at the copy method. All right. So we define the function do copy. It's a virtual method. It's defined virtual in the base class, so you don't have to keep putting the virtual keyword there if you don't want to. And it's going to take an argument, which is the right-hand side of the equation, right, if you will. So the first thing we're going to do is we're going to cast the argument to something of the type that we know, because that's the type that we're looking for, in this case bus item. And if that doesn't work, then we're trying to copy the wrong type of object, so we report an error. Right? That's a pretty typical kind of thing that you would do. And then what you do, you call super.doCopy. So that means if this thing is extended from any other sequence item, you're going to get the base class copied as well. And then you define for yourself whatever needs to copy from one side to the other. Right? So we're going to copy the delay, the address, the opcode, the slave name data, everything from the right-hand side to the new object. Right? And that's it. Okay, so when you go and use this, you're going to say, okay, I have two bus items, A and B. So I say A.copy of B, and what that's going to do is it's going to take the contents of B, and it's what we call a deep copy because we're doing super.doCopy, right? So everything that's in B is now going to get copied into A. So A now has a copy of all the information that was in B. Now this assumes that A and B both exist, right, before you do this. There's another method called clone, which actually uses the doCopy method underneath, but what clone does is that it actually creates a new object for you. Okay, so when you say b.clone, that will create a new object with the contents of B, and then you can copy that, you can cast that object into A if you want, right? So both of these operations wind up doing the same thing. It's just that clone actually creates a new object for you. Right? So depending on what you want to do, if you already have something existing, you copy. If you want something new, you clone. Okay? Right? And then we do something similar for all the other methods: compare, convert to string, print, record, pack, and unpack. So a word about phasing. So phasing is proving to be the bane of several people's existence, mine included. So this is something that we've been working on in UVM pretty much since its inception. Before we actually started UVM, we did a survey of people, and one of the top requirements for UVM was to have runtime phasing. It's turning out to be a lot more difficult than we thought, and so we're still not there yet. UVM 1.1a does not have a robust definition of phasing, but I will show you what it does have, and we'll talk a little bit more about what we're trying to do. And then I think I'll be in good shape time-wise. All right, so what we did in UVM was we added several new phases that are in parallel with the run phase. Right? So those of you that are familiar with OVM, this is basically the OVM phasing. There was one task called run that did everything that you need to do, and everything else were functions that either built your environment ahead of time or let you figure out what happened at the end. So we wanted to keep backward compatibility, but we wanted to give you the opportunity to kind of have a better handle on subdividing things. So rather than everybody trying to write their own sequences that would try to manage this on your own or do other things, we decided to create reset, config, main, and shutdown, and a pre and a post version of each of those. And then we tried to define what you should be doing in each of these phases. And the big problem that we ran into was once you start doing this, people naturally jump to the conclusion that you can then go from somewhere in here maybe back up to reset. Right? If you're in the middle of something and you say, no, actually I really want to start over again. Right? And once you start doing that, it opens up a host of other issues elsewhere in the UVM, most notably in the interactions between the driver and the sequencer. And then you have the notion of, well, what happens if some components were written to handle it and others haven't? So these are the issues that we're currently dealing with. The general consensus that we've come up with so far is that when using UVM, because these phases exist in UVM right now, right? So if you want to use them, that's fine. What we recommend, though, is that things like your driver and your monitor execute the run phase because they typically do the same thing all the time. Right? The config phase is, for example, setting up your device to do something. But the way that you do that is you send transactions to it, to write to registers or whatever. So the driver is doing the same thing in the config phase and the main phase, right? It's just sending transactions to the device. Right? So drivers and monitors typically execute run. We recommend using these phases to help you define, subdivide your stimulus. Right? So in any particular phase here, you raise an objection to the phase, you start the sequence that you want to do, however you want to do it, fork, join, whatever, and then at the end you drop the objection. So that's typically going to be what you would do in your test to execute specific sequences for specific phases. Drivers and monitors use run phase, and again, don't use phase domains or jumping. I believe Mark's going to talk a little bit about phase domains. They've actually been able to use them, but in general, there's a lot of stuff that you need to be aware of before you start doing that, so we don't recommend that you just jump into it. All right, so I just got a couple minutes here to wrap up. So objections are the things that we use to manage these phases, right? We want to make sure that if I'm doing something in main phase, that everybody has an opportunity to do what they want to do in main phase before we move on. So we use these things called objections. And objections get raised to say, okay, wait a minute, I'm not done yet, and they're hierarchical. So if the sequence raises an objection, that gets passed up to the sequencer, that gets passed up to the agent, and if somebody else raises an objection, that gets passed up to the agent as well. So the agent now has two objections. And then they get dropped hierarchically as well. So when the sequence drops it, it gets dropped all the way up. So now we have one outstanding objection in the agent, and then when the monitor drops its objection, now all the objections are gone and we can move on. Right? So typically the way you would do it is, for example, in your monitor, you're waiting for some transaction to occur, and when that transaction occurs, you say, okay, now just imagine for a second that this is the last transaction that we need to execute. Okay? So from the test perspective, it's already sent the last transaction. It's done. Right? But as the monitor, we say, wait a minute, there's a transaction going. I want to make sure that we don't move on until I finish processing this transaction. So I'm going to raise an objection. Say, wait a minute, hold on, don't do anything yet. I still got to do something with this. So I'm going to collect it, whatever that means, record as functional coverage, etc., write it out to the analysis port, and then I'm going to drop my objection. Right? So that's all well and good. That means that that last transaction is definitely going to get handled before we exit the phase. The only problem with this is that we said before that when all of the objections are lowered, then you're going to move on to the next phase. So what happens if the monitor is the only thing objecting? Well, if the monitor is going to object every time it sees a transaction, the first transaction comes in and raises the objection, says, wait a minute, then it drops the objection, everything's done, we move on to the next phase, and you've only done one transaction, right? So you need to be aware of that. So we actually don't recommend that you control the objections from a monitor. There's also performance issues about having a monitor raise an objection every time it sees a transaction. So what we really recommend is that you monitor, that you deal with objections from the test, right? And so in the test, what you would do is, again, for any particular phase, you raise your objection, you execute your sequences, and then you drop your objection. Right? Now, again, from the test perspective, that last transaction may have gone, so you may think you're done, and you may lower the objection, but what you want to be able to do is to provide everybody else a way to say, wait a minute, we're really not done. So going back to the monitor again, there's this method called phase ready to end, which basically says, okay, everybody else thinks they're done, are you okay with that? And the monitor says, well, it's not okay for me to end because I still have this last transaction going on. So it's an opportunity for the monitor to raise the objection to ending that phase. So now the monitor is only going to raise one objection when everybody else thinks they're done, do whatever it needs to do to that last transaction, wait until it's okay to end, and then drop the objection. All right, so this phase ready to end is a method that you will define typically for your monitor. You might also do it for your driver or your scoreboard. in there so that when everybody thinks they're ready to exit the phase, if you're still busy, you get a chance to raise the objection. Okay? So the way it works is when everybody's objection goes down, we call the phase ready to end on every component, and anybody that wants to raise the objection again can do it, and we wait for that to happen before we go and try to exit the phase. All right, so that's how you would do your monitor using phase ready to end. So it's just going along processing transactions as they come in, and it only deals with the objections when it has to at the end of a phase. All right, so again, the environment is the test bench. It defines what the components are there, what components you need to verify your device. It can set defaults, including sequences to run, what coverage you want to use. The test then tweaks the test bench, right? So it sets configuration, it sets factory overrides. It may define additional sequences to run in parallel with the background sequences. This is a pretty typical thing that you would do. And then the other thing that is most important for the test to do is to make sure that the simulation actually ends. All right? I don't want to get any support calls saying my UVM simulation is running forever, because the first question that we're going to ask you is, did you drop your objections? Okay? So do that first, and then we'll talk. All right? So again, just to show you, so in the test here, you have the environment, the environment's config, the agent configs, right? So these are the things that the test worries about. How am I going to configure the things that I'm going to deal with? So in build phase, you create the config object, you define it however you want, you set it using the configuration database so that later when the environment comes up, it has something to go look for, and then you create the environment, and that's all you need to do in the test. Right? That configuration object can include sequences to run in the background or configuration for agents or other things in there. That's the base test. And then what we do is we extend from that base test. So the base test does all the piddly stuff, right? The stuff that everybody has to deal with. But the actual test is then extended from that base test. And this is where we define the interesting stuff that we're going to do. So we're going to create a specific sequence that we want to run. And John will talk more about this. But again, in build phase, you call super.build phase to build what you define in the base test. And then in the run phase here, and again, it could be main or whatever, I'm going to actually create my sequence, and I'm going to raise an objection. I'm going to start my sequence, and then when my sequence is finished, I'm going to drop my objection. All right, so this is now the test code, right? This is it. It's what interesting stuff is in my sequence, and how am I going to run my sequence? Okay, this is typically what a test looks like. You may also change some of the configuration stuff for the environment or the agents as well. But it's really just a few lines of code here. All the work really is being done in the environment. Right? So the test really just tells the environment what to do. All right, and then to invoke the test, we can set the virtual interface that we're going to use from the top level module up here. Right? And we can use the configuration database to do that. And then we call run test. Right? We call run test with no arguments, and we specify which test we're going to use on the command line. Right? And then run test will actually take that string name, whoops, wrong button, right? It will take that string name and create an instance of it from the factory and then start executing it. All right, so again, the environment is typically complex. It's as complex as you need it to be. If it starts getting way too much, you can simply stop, create an extended environment that has additional settings or what have you, and just pull that from the factory. So the environment sets up the agents and other things. The test typically is going to be embodied in a sequence or a virtual sequence that will control everything else that happens. And you can have a default one in the environment if you want, and then the test goes in and simply tweaks things. So it chooses the sequence to run, it controls the coverage and the scoreboard that you're going to use, and typically those are related to the sequence that you're going to execute. Right? So if you say, okay, I'm going to run a sequence that's going to execute these things over here, you don't want to instantiate a coverage object that's looking at these things over here. Right? They need to match. So that's one of the things that the test has to do. The environment itself, as I said before, is a component. Right? So you can configure it as necessary, and then you can reuse it. Right? You can take that, component, put it in a higher level environment. So if you have one environment at the block level, when that block goes into the system, that environment becomes a component in your system level test bench. Okay? And that applies to everything, and you can configure it as necessary, because the key is everything that you've written, every component, every environment is written to be configurable. So it doesn't matter whether you configure it directly from a test or whether it's configured from another environment that instantiated it. Okay? All it knows is it's being configured to be used somehow. So every component that you have becomes application specific and configurable for your particular test bench needs. Okay? So then you wind up stringing these together as you build your system, and this becomes your system level test bench, is a bunch of block level environments that get strung together, connected as other components, right, as you need them. And then if you take that block and put it in a different system, right, you have that same block level environment here that was specific to this particular block, but now that since it's in a different system, this environment is going to be in a different top level test environment. It'll probably be configured somewhat differently, but it's still there. It still works, and it can be configured for whatever particular application you need.
Well, as some of you guys know UVM already, and some of you, I think, don't know UVM already. For those of you who don't know this stuff already, don't panic. If by the end of this morning you're feeling just overwhelmed by everything we've thrown at you, that's perfectly normal, right? So generally it takes us 3 days to teach folks UVM. And at the end of 3 days, folks usually say, that was hard work. I wish we could have had a longer training class. And today we're doing this in one morning. Right? So if you've not done this before, it's going to be heavy for you. So what we've got this morning is 4, I guess, very different styles of presentation, where we're going to throw all sorts of different stuff at you of what is quite a big subject. And I hope with some very different styles of presentation, each of you will be able to get something out of it. So I'm going to talk about TLM communication, sequencer driver communication, structuring sequences. So first off, TLM. So in talking about TLM, what I'm going to try and do really is to give you a vocabulary, a lexicon. I'm going to talk about the main concepts in TLM within UVM so that you can recognize these things. So now I'm giving you permission to relax, calm down, take a little nap if you like. You don't have to concentrate too much. I'm going to ask you to wake up again when I talk about sequencer driver communication, right? So 20-minute lull, just calm down, let it wash over you, just try to get some of these ideas, and then I'll wake you up a bit later on. So Tom has introduced very rapidly in this great quick-fire presentation a lot of information, a lot of concepts about UVM. So that we've seen in UVM, we separate tests from the verification environment. There's a standard way of organizing a verification environment, including one agent for each of the main interfaces to the design under test. And I guess many of you are familiar with this already from UVM or OVM. Everything you can see on the screen here is quasi-static. If you're writing this in vanilla Verilog or VHDL, these would be module instances. You do these things once. In UVM, you do them once. You do them once dynamically at the beginning of simulation and set up all of this structure at the beginning of simulation. So everything you see here gets created during the build phase, as Tom outlined, and then connected together during the connect phase. And then stuff happens dynamically. So dynamically, we have sequences running on sequencers. We have transactions communicating between components. And that's the area that I'm going to cover. So I'm going to initially talk about communication between these components using transaction level modeling. Then I'll talk about how the sequencers work. So, transaction level modeling ideas. So transaction level modeling in UVM was inherited from the system C world, from the TLM1 standard. Incidentally, TLM1 now is an official IEEE standard. As of the latest release of the System C standard, TLM1 is included in the IEEE standard. So if you care to defect to the other Accelera tutorial stream this afternoon, I'll tell you all about the new System C standard. So TLM1, message passing. The idea of the TLM1 standard, which underpins communication in UVM, is the idea of message passing, where you're essentially throwing stuff over a wall. So when we communicate between components in UVM, we're sending communication over a wall. And the point is that the only way that these two guys are going to communicate is by throwing stuff over the wall. No shared memory, in other words. They're not sitting side by side looking at some shared information. All the communication is at arm's length through message passing. So that's the first concept that underlies TLM1 communication. Then within UVM you see all of these methods: put, get, peek, try put, try get, try peek, write. That's the basic set of method calls that are going to be used for communication. Put, get and peek are blocking. Try put, try get, try peek are non-blocking. Blocking means you wait for an answer. Non-blocking means you don't wait for an answer. You just carry on immediately. So let's just look at put, get, peek, these blocking calls. The idea of put, get, peek is that they don't lose any transactions. So when we use put to push some transactions between two components, we're guaranteed not to overwrite any transactions. So put, get, peek, basic communication in TLM1 and UVM, doesn't lose any transactions along the way. When we put a transaction, then the target is going to wait around until it's able to accept the transaction and only return from the put call when it's finished, when it's able to receive the next transaction. And the same for get. So get is used to pull a transaction, and the target will only return when it actually has a transaction to provide. So again, no transactions get lost along the way. Put, get and peek work with streams of transactions where no transactions get lost along the way, everything's ordered, things only proceed when all parties are ready. So that's the basic idea of this TLM1 communication. A lot of communication is mediated by a third party, some intermediary. That was the case in VMM. Those of you who come through VMM will recognize this as being similar to a VMM channel, also a FIFO in many forms of communication. So with a channel or a FIFO, a producer might write transactions into a FIFO or a channel. A consumer might get transactions from that FIFO or channel. So we'd have a push interface up the top here, a pull interface at the bottom, and in the middle we've got the channel or FIFO that mediates between the two things. That's not the native way that communication works in UVM. In UVM, the native mode of communication is unmediated. And this concept takes a bit of getting used to. So the idea here is that a producer is pushing a transaction, shoving it down. Then the consumer doesn't pull transactions, it simply implements that method. So our producer is calling put. The consumer implements put down at the bottom here. Okay. So we can use these basic method calls to implement both push interfaces and pull interfaces. And this is an important idea that often causes confusion when people start looking at transaction level communication in UVM. So we can push transactions up at the top, or using get, we can pull transactions back the other way. And you see both styles of communication getting used in UVM, pushing and pulling. And the key point here in your minds as you start to understand all of this stuff, and as I said, don't think about too deeply now, because unless you've seen this already, you are not going to learn it all in 10 minutes. The key thing to remember here is that the control flow and the data flow can be going in opposite directions. So with a push interface, we're pushing data from left to right and calling functions from left to right. With the pull interface down at the bottom, we're calling the function from left to right, but transactions are flowing from right to left, the other way. So with a push interface, control and data are going in the same direction. With a pull interface, control and data are going in opposite directions. What happens then in TLM1 land is that the actual connections between components, between producers and consumers, are done by instantiating so-called ports and exports. And if you've done VHDL or Verilog together, you can think of ports as just being analogous to ports in Verilog or VHDL. In UVM, they're a little bit different because although they're analogous, they're used for communication and for separation of concerns and all of those good things. What we actually do through ports and exports is make function calls, method calls. So the producer is going to make a call to a put function through a port. The consumer is going to implement an incoming function through an export. And what the port effectively does is to state that the producer requires an interface. And we're jumping off into the object-oriented software world now. But when you choose to use a port on a component, what you're really saying is, I want to use a particular service. I require a service that's going to be implemented by the method that we're calling through this port. And when we use an export on a component in UVM, we're saying, I'm providing a service. And for many people, this kind of seems the wrong way round. But we're requiring a service which is implemented by a method, or providing a service that's implemented by a method. And then we can form a kind of contract and actually say, great, somebody's providing a service, somebody else is requiring a service, let's get them to shake hands. And then they can talk happily together. And that's done in UVM by connecting a port to an export. So when you see scattered throughout these slides this connect method, what you're doing is connecting together a component that requires a service with a component that provides a service. And then hopefully everybody's happy. Another thing that you'll see scattered throughout these slides and UVM documentation is the distinction between ports and exports and imps. All of these things, ports, exports, imps, these guys are all used to forward method calls. What happens is that ports are used to call methods up and out of components. Exports are used as method calls are coming down and into components. And then the end of the line is the so-called imp. And an imp isn't a mischievous little elf with pointy ears. An imp in this case stands for an implementation. So imp is short for implementation. And the implementation is the end of the line. So when you hit an imp in UVM, that means you're going to find an actual implementation of that method, put in this case. So the guy on the left is calling a method through a port. Method calls go up and out through ports. Hop over at the top level from port to export. Down, down, down through the hierarchy until we end up at an imp, which is the place where this method is actually implemented. So this is what it looks like in the source code. As we've seen this before, Tom went over it briefly earlier. We have a build phase method in UVM where we're creating the child components. Then a connect phase where we actually establish the connection between port and export. And you'll see lots of examples like this kicking around. Then finally in this first section, analysis ports. So analysis ports are one of the commonest forms of port and export that you use when you start to learn UVM. An analysis port is just a port. It's a particular flavour of port, but it's a port that's used to implement a broadcast mechanism. So the difference between an analysis port and a regular port is that an analysis port could be connected to a single export, or it could be connected to no exports, or it could be connected to multiple exports on so-called subscribers. So analysis ports and analysis exports are just ports and exports, but they implement a broadcast mechanism. So if we've got a monitor embedded in an agent and it's shooting transactions out to the rest of the verification environment, The monitor doesn't know or care how many other components there are in the verification environment listening to it. So you can just put an analysis port on a monitor and then forget about it. If you don't connect it up, that's fine. If you connect it up to one subscriber, one listener, that's fine. If you connect it up to many, many subscribers, that's fine. They all get a copy of the transaction. So an analysis port is just a broadcast mechanism. Okay, that's the end of part one. Now I'm going to ask you all to wake up again from your slumbers as we start looking at sequencer driver communication. Because hiding in this section is what I'm thinking of as the crown jewels of this particular presentation. There's the cool stuff going to come up now in this section, where I'm going to try and tell you why we're doing all of this in the first place and what's so good about it and what it's really all for. I'm sure a lot of you get fed up with new verification methodologies coming out in new languages and all of this stuff that you've got to learn. What's the point of it all? I mean, the point of it all has got to be something that actually allows us to do our jobs better or save money for our companies or be more productive. And I'm going to try to illustrate in this section one of the key points about UVM that can help make us all more productive. We'll get there in a minute. So sequencer driver communication. So this is a fragment from a lot of the diagrams that we've seen already today. Sequencers communicate with drivers. Drivers are connected to the design under test, actually through a system Verilog interface, though I'm not going to go into that in lots and lots of nitty-gritty detail. The thing that we'll focus on is the communication between the sequencer and the driver. So the driver has a port. The sequencer has an export. The ports and exports are actually built into these components. They're implicit. Sequencers run on sequencers. So drivers and sequencers are quasi-static. They're components. Sequences and transactions and sequence items are dynamic. They're created at runtime. They're running on tops of these things. And the actual communication between the driver and the sequencer is through a port and an export, using the sorts of mechanisms and concepts I've just been talking about. So let's focus on that. This is what a sequence looks like. So a sequence is a class. It represents a dynamic object that's going to get created on the fly. It's got the usual ingredients of a class and the usual ingredients of a building block in UVM that you'll see thrown at you again and again today. There is now plenty of tutorial material on the web on giving you basic introductions to UVM. So if you come to the end of this morning thinking, wow, that was drinking from a fire hose, that was all too much, go back and hunt on Google and you'll find lots of tutorials out there by Tom and myself and other people giving you introductions to all of this stuff. So here inside we've got a sequence, we've got a constructor. Every sequence has a body task. The body task does the work of the sequence. And this particular body task is making a standard incantation, a standard series of magic spells to actually talk to the driver. So it creates a transaction, then calls start item and finish item in order to handshake with the driver. If we look at the driver itself, but before we look at the driver itself, if you want, you can do that with a macro. So one of the frequent topics of discussion in the UVM world is whether macros are evil or not. If you happen to think macros are evil, then you can do without them by just making function calls, create start item, finish item. If you'd rather wrap this lot up in a macro, you can call UVM do with. I won't get hung up on that. We can do it either way. Now let's look at the driver. So the driver, for its part, is going to pull transactions down from the sequencer. So it calls get next item to get a transaction down through the sequence item port, raises an objection, as Tom described earlier, as it wiggles pins, and then calls item done when it's finished. So here in our driver, we've got a call to get next item followed by item done. Get next item is a variant on get. I introduced get a little while ago, and I talked about get as being one of those TLM1 style calls to grab a transaction. Get is a simple blocking TLM1 method call. Get grabs the transaction. It only returns when it's got the transaction. So when get returns, the transaction is over, finished, job done, nothing else to say about it. Get next item and item done is a bit of legacy, which I think I first saw in something very like it in ERM many, many years ago. So this is a bit of legacy stuff that's got inherited inside UVM. Get next item and item done effectively splits get into two parts. So get next item waits for the transaction to become available, and then when it returns, the transaction is held open until the driver calls item done. And when the driver finally calls item done, that effectively finishes off the transaction. And in UVM, you've got the freedom to do it both ways. I kind of agree with Tom here that freedom is a bad thing. We don't want two ways of doing it, but we've got two ways of doing it. Darn it, this is the way it is in UVM. So we can call get next item, item done. Get next item grabs the transaction. The driver fiddles with the transaction, and then when it's finished, it calls item done. Or we can do things TLM1 styley, and the driver can call get, and then get only returns when it's finished. Okay, now let's move toward the crown jewels here. Let's have a look at how all of this stuff really works. And I did agonise about whether to show you this slide at all, because it's rather nerdy, to be honest. It's down in the bowels of UVM, seeing how the engine really works. But let's have a look at it anyway, because I think it's worthwhile. So we've got a sequence running on a sequencer communicating with a driver. Sequence on the left, driver on the right. So the sequence creates a new transaction that it's going to send through to the driver, and then calls start item to say, I'm ready to send this transaction to the driver. The driver, meantime, at some point comes along and calls get next item. So the driver calls get next item, the sequence calls start item, and here in blue we've got the first synchronization point. And this is in the engine within the sequencer that's communicating between sequence and driver. So the sequencer waits for the sequence to be ready to generate a transaction, waits for the driver to be ready to suck a transaction. Here there's a synchronization point. When both parties are ready to communicate, then we drop through and a whole bunch of stuff happens. So what happens then is that we return from start item. The sequence then gets to randomize the transaction. Sequence then calls finish item, and get next item returns with that newly generated transaction. So we drop through between these two blue boxes, which are the two synchronization points between the sequence running on the sequencer and the driver. And what this is actually implementing is an approach called late randomization. What you're seeing here in action is late randomization. And that's a deliberate philosophy, a design decision built into UVM for how to do constrained random generation. So the idea is in generating a random element, either in the structure of the verification environment or in the traffic that's generated, we wait to the last possible moment before actually randomizing transactions. And the point about waiting to the last possible moment is to have maximum flexibility in randomizing those transactions and allow us to take into account anything that may have changed in the meantime. So you use the very, very latest state of the DUT and of the verification environment in randomizing transactions. That's late randomization, and that's implemented by having this two-stage handshake here between the sequence and the driver. So the sequence creates a new transaction, says it's ready to go. Only when the driver is ready to get that transaction, when everything's ready to go, both parties are ready to talk, only then does the sequence actually randomize the transaction and then drops it through to the driver by returning from get next item. And then we wait for the second synchronization point, wait for item done. And what we're doing now is waiting for the driver to finish with that transaction. So the driver is busy wiggling pins, it's still holding that transaction open. When the driver now calls item done, the driver has now finished with that transaction, and we can drop back through and finish off. So the stuff in blue are the two synchronization points here, inside this mechanism of the sequence communicating with the driver. So I hope I've unveiled a little bit of mystery from that key mechanism in UVM where sequences run on sequencers and they communicate transactions to drivers that then wiggle pins. Now the crown jewels, the bit in gold here. These, well, they're meant to be gold. They could be kind of muddy brown coloured boxes here. These are the callbacks that are part of this whole handshake between the sequencer and the driver. So we've got a bunch of callbacks here, pre-do, mid-do, post-do. They're built into this handshake between the sequencer and the driver. And they give you a chance to go in and interfere with what's going on here, to actually customize what's happening, to insert your own code. Now, why would you want to do that? Well, now we come right back to the whole reason for the existence of UVM in the first place, which is, of course, enforcing best practice, allowing you to stand on the shoulders of giants and take advantage of all the good things that have done before, but also verification IP reuse, to reuse bits of verification IP. So imagine, if you will, all this code here built into a piece of verification IP. So you go out on the internet and you surf to try and find a sequence library for your favourite protocol that you're using. And you find one probably written in Eastern Europe somewhere, and you go buy it, give your credit card details and grab your code or however it works, and get a piece of verification IP from your favourite protocol. You probably won't get source code. You maybe get some object code that's compiled. There'll be sequences in there, and if we were to look at the source code for the sequences, this is what they'll say: create, start item, assert, finish item, standard UVM code. You now come to write your own test, your specific test, the test that's specific to your verification environment in your application, using this sequence that you've bought from Eastern Europe. So you can create your own sequence, and in your own sequence you can change the behavior of this existing sequence without having any access to it. How do you do it? These callbacks, these gold ingots here that are built into the sequencer driver communication. We can actually override the behavior of the sequencer driver communication. So here we go. We've created our own sequence by simply extending the sequence that we bought. So we take Eastern European sequence, we extend it by overriding mid-do and post-do callbacks to fiddle with the communication, with what's actually happening in the communication between the sequencer and the driver. So mid-do is peeking at the address in the last transaction, and post-do is storing an address in the transaction. So each time a transaction is generated, we're snooping its address, storing it in a variable, and then when we generate the next transaction, we're using the address of the previous transaction to constrain the address of the next transaction. So we're actually reaching in and constraining the traffic between the sequencer and the driver. It doesn't matter, whatever you want to do, totally user customizable. The point is that we've modified the behavior of this sequence without even having access to the source code, without recompiling it, without anything. We've just reached in and changed its behavior. And I have a lot of trouble when I'm running training classes trying to persuade people that this is a good thing. I say, but why didn't you just change the behavior of the sequence? I mean, why didn't you just take this thing and write it? What's such a big deal about this? Because you don't want to start hacking other people's code. Because if you hack other people's code, what are you going to do? All together now, those of you who have done it already? You're going to break it. You are going to break it. You just will. Sooner or later, you just will. You don't want to hack other people's code. You want to take it and just use it. And that's what we're doing here. Here we're using an object-oriented programming style to do it. Those of you who came up through E would know you do the same thing there in an aspect-oriented style. It doesn't matter. What we're doing in either case is we're using the best of software development methodology for hardware verification in order to take an existing functioning component and changing its behavior without breaking it. So that's what we're doing here, changing the behavior. Now we can say use this by actually doing a factory override. And Kathleen's going to talk more about the mechanism here of factory overrides later on. Here I hope I'm motivating why this is cool stuff. So we can call set type override to say every time anybody creates my top sequence, instead replace it with one of these. So what's going to happen here is that when create gets called up here in this line of code buried in this bit of Eastern European verification IP, then we're actually going to be replacing that with our own version of the sequence. So what actually happens now at runtime is that finish item gets called. As finish item is called, finish item is calling the callbacks that are built into it. We've overridden the behavior of those callbacks. So we get to insert our own code in the dynamic execution of this bit of predefined verification IP. Okay, so let's move on to the final part of the presentation, structuring sequences. So there's a bit of machinery here I'm going to describe. I'm not again expecting you to remember it all. That's why we have run training classes, and there's lots of stuff on the web you can go look at. But I will just try to highlight how UVM allows you to build constrained random sequences out of other sequences. So let's start off with the boring machinery. We can start sequences. Here we are starting a sequence from a test. So run phase is one of those standard phase methods that we've already referred to today, that Tom talked about in particular. So here within a test, we're creating a new sequence by just using the factory method create that Kathleen's going to explain later on. Then we're finding ourselves a sequencer to run the sequence on and starting the sequence on the sequencer. So this is what the code actually looks like to start a sequence on a sequencer. Not a big deal. We can start sequences from other sequences. And again, using create and start, the code is very, very similar. So here within the body task of a sequence, we're creating a new sequence and we're starting that sequence by calling it start method. And you can go look up the nitty-gritty detail of what all of these arguments mean. Or if you'd rather do this with macros, we could use a macro to do the same thing. So we can explicitly call start, or we can call UVM do. So UVM offers two different flavors of API. There's a function-oriented API with a bunch of methods like create, start item, finish item, start, or there's a bunch of macros. They're interchangeable. So now let's go back to the diagram and see what's really going on here. So we can start sequences on sequencers. Those sequences can be started from a test. So remember, Tom described the verification environment, which is large, complex, created by verification experts, big body of code. A test then reaches in and tweaks that verification environment. So a test could reach in and tweak the verification environment by starting a sequence on a sequencer. Or another sequence could run a sequence on a sequencer. So sequences can start other sequences. So sequences can be nested. Sequences can be layered to create complete protocol stacks. Or you can have sequences that run other sequences on other sequencers, so-called virtual sequences, that I'll describe briefly later. And a sequence can be totally directed and deterministic. A sequence could execute a very specific set of instructions to do something particular. Or a sequence could be completely random, or it could be anywhere in between. It could be constrained random. And a technique that's very often used here is so-called knobs or control knobs. So control knobs, well, think of any piece of audio equipment. Think of your amplifier or something that generates a sound, and you've got a whole bunch of knobs on the front, and you turn the knobs and it makes different sounds, right? Signal generator. Think of that kind of thing. So knobs are parameters that control what happens. So maybe you turn the knob to one extreme and you get a totally directed sequence that does something very specific. You turn the knob to the other extreme and you get a totally random sequence. Or you can tweak these knobs to shape the traffic somewhere in between. That's the kind of metaphor that we've got here. So let's have a look at how we can structure those sequences when we're calling sequences from other sequences using so-called control knobs. One of the ways that we might want to control all of this stuff is through the configuration database. So Tom referred to the configuration database earlier, and Kathleen's going to give you a full nitty-gritty account of it later. This is one reason why you might want to use it. So the configuration database is really a great alternative to global variables. It just means you can stick parameters in a configuration database and then use them to customize the behavior of your verification environment. So a test, for example, could write the values of these control knobs into the configuration database, and then our sequences could read those values back again. Anyway, that's an aside. Let's have a look at the sequences. So here is a sequence that does a memory burst read. So if we look in the nitty-gritty here of the sequence body, it's generating instructions, a move instruction, move high, load op, add op, and so on. It's generating very, very nitty-gritty instructions to do a memory burst read. from a given start address and of a given length. So the start address and the length are the control knobs here. If we were generating a directed sequence, we could put in very specific values for start and length. If we just wanted to get this to do something to get our design up and running, we could completely randomize these, or somewhere in between. So what we're going to do is somewhere in between. So here's a sequence memory copy that's going to run a memory burst read followed by a memory burst write. So here we've got one sequence that's invoking lower level sequences, nested sequences. The previous sequence, mem burst read, is getting called here inside our memory copy. We're doing a burst read and then a burst write, constraining these control knobs. So we've got some system Verilog inline constraints here to set the values of our knobs, start and length. But we don't set them to precisely determined values, we set them to randomized values. So start and length here are randomized fields. They're going to be randomized, and we're constraining them to have the values of address 1, address 2 and size, which are also randomized variables, but we're constraining those randomized variables. So we're actually constraining these things to work so that the memory bursts start address aligned and their lengths are address aligned as well, using these constraints. So we've used constraints, system Verilog constraints within our sequences, which are just system Verilog classes, in order to constrain the values of these control knobs that are being used to establish the relationship between different sequences. And we're then running all of those sequences on a sequencer. And as each of these sequences is running, buried here within this UVM do with macro, we've got the sequence side of the sequencer driver handshake that I described earlier. So here, when we do UVM do with and run burst 1, I guess I need to go back to my memory burst. We're going to be coming and executing this code, generating these requests. And inside here, we're calling start item, finish item, and we can actually insert our own callbacks in there and modify the behavior of all of this stuff. So there we go. Finally, virtual sequences. Well, virtual sequences, to be honest, aren't a big deal because they're just sequences. A virtual sequence is a sequence used in a special way. Those of you who go back as far as OVM will remember that in OVM, virtual sequences were a distinct class. So you had virtual sequences and virtual sequencers as a different kind of thing. In UVM, they're not. A virtual sequence is just a sequence. A virtual sequencer is just a sequencer. The application of virtual sequences is coordinating the behavior of multiple agents. So if you remember, agents are the basic building blocks of our verification environment. The agents have a standardized structure that you'll see again and again today, including a sequencer on which we're going to execute sequences. So these agents may be specific to a particular interface on the design under test. So this sequence is going to be specific to a particular protocol, the protocol supported by that particular interface. And then to coordinate the testing of our complete chip, we're going to need to coordinate the sequences running on these different sequencers. And we do that from a virtual sequencer. So a virtual sequencer runs a virtual sequence, and a virtual sequence is quite simply a sequence that doesn't itself generate transactions. So a virtual sequence is just a sequence that runs other sequences. And you've seen all the code to do that already. It just calls start. So the virtual sequence here just calls the start method of a sequence to run that sequence on another sequencer. We would just have to do a bit of messing around when we instantiated our components here in order to make sure that this sequencer actually knows where these sequencers are. So during the connect phase, we'd make sure that we actually connected up variables here, so our virtual sequencer knows where the actual sequencers are, and then the virtual sequence running on the virtual sequencer can actually start sequences on lower level sequencers. There is a lot more to this story, so if you go hunt around in the UVM documentation, you'll find there's a whole bunch of interesting methods for controlling the behavior of sequences on sequencers. So if you've got multiple sequences running on the same sequencer, you can prioritize their behavior. You can define arbitration algorithms. You can say some sequences have a higher priority than other sequences. You can even have a virtual sequence reaching in and grabbing exclusive access to a particular sequencer. So you could have some background traffic generators here, generating traffic on a particular instant interface on the DUT, and then have a virtual sequence reaching in, grabbing exclusive access to that sequencer, blocking all of that background traffic and generating traffic specific to one test on that particular sequence.
To talk to you about some of the things that are part of UVM that allow you to customize your environment. A lot of these concepts have already been touched on, and these are sort of the heart and soul of what UVM is all about. So, as Tom mentioned earlier, UVM provides guidelines for creating reusable verification components, and the library provides base classes and standard API for creating verification components that you can use to verify your design. The key thing about UVM components is the ability to configure these, and as John mentioned, you want to create a component that's flexible enough to make changes to it from above. You don't want to go inside and modify your code every time that you want to maybe run a test that has a small modification to the standard behavior. So UVM components are modified from above. Things that you might want to do is configure an agent as an active or a passive component, so this would affect the architecture of the test bench. You might want to determine the number of masters and slaves, disable checking, enable checking coverage, and things like that. And then also we have this concept of sequences that generate random stimulus, and you might also want to use some way of modifying the stimulus for a particular test. So next I want to just cover some of the aspects of your environment that you might want to change. One thing you might want to do is change the architecture of the test bench when you're creating it at time 0. So you want to specify the number of slaves, the number of masters. You want to specify if components are active or passive. And then a key thing that you want to do is specify the virtual interface connection, which is different for each design. You might want to set some default parameters, legal addresses for slaves. And then you also might want to specify specific constraints for a test. You might want to, do a constraint test where you're making your delays very short or something like that. Those of you in the back, you can't see the bottom of these slides because I was sitting back there earlier, so I'm going to kind of cover the buttons on the bottom of the slide a little bit, make sure I get those covered. But one thing you might want to do is turn off checks in your scoreboard, or you might want to change the verbosity of messages that get printed. So once you have a simulation running and you want to just focus on a specific area of the design, you can alter the verbosity without going in and changing code or doing a tick define or something that makes you have to recompile everything. Things that affect the architecture of the design have to be set before you start creating stimulus. So those are the kinds of things that have to be set up before you actually run any stimulus through the design. And then the ones on the bottom are things that you can actually change during runtime. So UVM provides facilities for customization. All of these have been touched on, some of them have been touched on in the earlier presentations. There's an elaborate configuration mechanism that's part of UVM. There was a lot of discussion about the factory. Messaging is the standard way of printing informational messages and errors and warnings. There's a mechanism that's built into UVM for messages. We talked about callbacks a little bit earlier today, so we're going to go into details on these items. So I'm going to start with an overview of the configuration mechanism. So when you want to configure a test bench, again, this is going to affect the structure of the test bench. So for example, there's an isActive property which is built into an agent, and it determines whether the driver and sequencer are created in a active component. You can also affect the stimulus for your test. Again, as I mentioned earlier, you want to make these changes from from above. You don't want to go in and modify your actual code, especially if it came from Eastern Europe. You don't want to mess with those people. Just kidding. My new manager is German. He's European. Okay, so configuration properties have to be set before the components are created. So again, you might want to specify the number of agents, master agents. And you don't want to pass this information from the top through arguments to a constructor or to the build phase. So why wouldn't you want to, does anyone want to venture why you wouldn't want to specify configuration information from as arguments to the constructor? Yes, John. Well, okay, so you can't use the factory, but the other thing is, as you build your test bench into larger and larger, you start with a component, and then that gets into a agent, and then an agent is part of a component becomes part of a test bench. You would actually have to pass those configuration arguments all the way through, and then your constructor becomes a giant mess. So it's better to pass them using these special mechanisms that are part of UVM. So one thing that we mentioned is this configuration database. It's actually built on top of something called a resources database, which is part of UVM. So the underlying structure is this resources database. Our recommendation is to use the configuration mechanism or the configuration database, which is built on top of that. It's a global resources database that implements the configuration mechanism. Any UVM object, so anything that's derived from UVM object, can access the database by looking at some sort of scope, and then a name, field, and then a value. So somewhere in your design, you may want to set a value or set a configuration. So you use UVM config DB, and then you parameterize it with the type. And then you give it a hierarchical path or some sort of scope, which is a combination of this, which would be the current scope, and then any subsequent string across that. That can have stars and question marks and things like that. And then you specify the name and the value. So when you go into getting, so that gets stored into this configuration database. And then on the get side, any component that wants to grab that out calls the get function. UVM config DB, again with the type. You do the get, and then you say this because you're getting it at that hierarchy, at that point in the test bench. Again, and then you try to match the name and the value. One more point here. All of the UVM config DB calls are static. All these functions are static, so you have to use the : operator when you call them. So the get and the set. So what does the syntax look like? So the syntax is UVM config DB, and then you specify the type. This again extends for the resource from the resource database. Then there's a set function, a get function. You can do an exist function that will check to see if if it exists in the database, it returns a value. You can dump it, and you can also wait for it to be modified. So that's a nice thing that you can do, is you can wait, for example, for a configuration to change and then act on it, and that one's a task. So just a note for anyone who used OVM or UVM EA, there was a configuration mechanism for components, and we had set config int, set config string, and set config object. Those are actually still part of UVM, but they're on top of, they're a convenience layer on top of the config mechanism. So you can still use these if you like to. They're still there. They've also created UVM config int, UVM config string, and UVM config object if you want to use those too. Okay, so how do you set a configuration property in a test? So for example, inside of your test, inside of your build phase, you you want to set an agent to be passive, so you say UVM config db UVM bitstream t, and again, I would recommend using UVM config int in this case. The scope, which would be this, and then from the test, the env.agent, you want to set the isActive flag to passive. And then on the get side, then you create the environment after. So you always want to call super.build phase. If you forget to do that, you don't get the apply config settings. So make sure you always call that. Your environment, your env build phase will be called after the test build phase. So it's, again, I think Tom mentioned it's top-down building. And then inside of your agent is going to do, inside of his build phase, he calls apply config settings in the super.build. So in the super.build of the agent, he will actually get, well, this is inside the env. He will get anything that maps to the env, and then in the agent, it would actually get the active passive, the isActive flag. So here's the agent. There's two ways of doing this. One way is to use apply config settings. This is built in when you automate a signal. So here I have the isActive flag, which is built into an agent now. So UVM agent includes the isActive flag, so you don't actually have to put it in your agent. So if you automate the isActive flag, when you call inside the build phase, when you call super.build, it will automatically apply any config properties that have been set for those fields that have been automated. So the isActive is automatically set during super.build, and then when it goes into the build phase, the isActive flag is already set, and it will create the driver and sequencer. The other way to do this is you can call the get explicitly inside of your agent. So in your agent, you don't have to automate that signal. You still want to use the UVM component utils, but you don't have to automate that field. And in this case, you call the get. It will check to see if the field has been set, or else it'll just use the default value. Okay, a very important place where you want to use the configuration database is for setting your virtual interface. Tom already went through this in his slides, but I'm just going to reiterate it again here. Inside your monitor connect phase, for example, you want to call the get of the virtual interface that you're trying to assign. Just one note here, you want to use UVM error instead of UVM fatal. This is a recommendation, because what will happen is if you have UVM fatal and you have your virtual interface connections or anything like that, we're using UVM fatal, it's going to kick you out of simulation and you're going to have to do them one by one. So use UVM error for those types of mistakes. So then again, as Tom mentioned, in your in your top level module, you have your instance of the interface, and then the set call uses the virtual UBus interface set again, and you have to match the type, and you set the interface using that syntax, then you run the test. So this is a very good use of the configuration database. Setting in the top instead of inside your test bench, for example, it removes any kind of dependency in your test bench. And then you can put your test bench in a package if you like. Okay, so that was the configuration mechanism. The next thing that I wanted to cover was the factory, and kind of give you the high-level aspect of that. Just remember, the good thing about UVM is all the stuff is built in. You just have to know how to use it. All the guts and all the weird stuff that'll blow your mind is built into the library, so you just have to use it the right way. Okay. Overriding component data for specific tests. So again, we want to be able to modify the behavior without having to go in and hack your code every time that you want to make a minor change or a major change. So for a specific test, you may want to further constrain your data items, or you may want to alter the behavior of a component like a driver with a modified version. you want to be able to exercise many different scenarios when you're doing testing. So you have kind of the default random behavior, which drives stimulus, but then you may want to go to a corner case, so you want to add attributes to classes add more constraint layering, and again, you may want to change procedural code. So for this, we have the factory. It's a classic software design pattern. It's classic software capability. You design your code, and then you defer until runtime the actual implementation or the exact subtype of the object that gets allocated. So, for example, we want to talk about constraint layering. So in a specific test, you have a data packet that has a length between 1 and 63, and for a special test, you want to hit a specific corner case where the length is less than 30. So in System Verilog, you can derive a subclass from the data packet called short packet and add new constraints. So how would you use this in a design? So let's look at an example. Here I have a simple data packet. It has a length and some data, and it has a default constraint of the length being between 1 and 64. And then throughout the design, you have a monitor which has a data packet. You have a sequence which has a data packet, and you have a scoreboard which has a data packet. And they're all constructed somewhere inside of that component. So for my short packet test, I want to add one more constraint and make the length of the packet to be less than 20. So if you wanted to use, traditionally, if you wanted to use this short packet, you would have to go throughout the design and change data packet to short packet throughout the design. So in the monitor, the scoreboard, and the sequence, you would have to make changes to the code. Sorry, this goes all the way to the bottom, so you can't see it. It says you'll need to change data packet to short packet equals new, everywhere throughout the design. So what we have instead is this factory, which is a central location for creating class instances. As you, each type that you want to be part of the factory is registered with the factory. So as you compile these things, the data packet and the short packet get compiled into the factory. When you create an instance, you use the create method instead of the constructor, the new method. So whenever you have a create in the design, it calls this create, this factory create. I think I have this messed up. Yeah, so if there's any override specified in the test or the test bench, it'll specify that we're going to override data packets with short packets, for example. So we have an override instruction in the factory that says make all data packets short packets. When you call this create function, it will check for data packet, do I have an override for the data packet? And it will return a type of the derived type. So in this case, it will return the short packet. So the factory, again, it's built into the library. Somebody did all the hard work to get this thing to work for us. So it's this mechanism for registering anything that's based on UVM object. You need to use the object utils macro for objects and the component utils macro for components. This will register that type with the factory, and it will define this create method. So whenever you call create, it will create a UVM sequence item or anything derived from that, so all your data will come from that. And when you have components, it will create UVM components and anything that's derived from UVM component. It's auto-instantiated at time 0, so you don't have to place this factory in the design, it's just there. And overrides can be called at any time. So if you specify an override halfway through the simulation, then the next call to the factory will create the overridden instance of the overridden type. So let's look at an example of using this create. You've already seen this on some of the slides, but this is kind of just reinforcing the concept here. So I have data packet extends UVM sequence item. Again, you have to use the object utils to add it to the factory. And then instead of using new inside your monitor, for example, where you're collecting items, you use this create function instead. And then if I override the value, if I override the data packet type with short packet, it will return the short packet type instead. And again, if you can't see in the back, all references should be, any kind of object reference should be created calling create instead of the constructor. And you just get in the habit of doing that all the time, and it's not a big deal. It's a funky syntax, but once you start doing it, it's pretty common. Okay, so again, just remember to use create everywhere. Stop using new, pretty much. Use it for all components and all objects, anywhere that you need to do that. So again, you can override the stimulus, and so how do you override? How do you do the setting of the override? So let's say we have a design with 2 agents and it has a data packet. So for a specific test, we want to replace all the data packets with short packets. So in the test or the test bench, you can say data packet : type ID : set type override short packet get type. So anywhere that you're creating a data packet, it will create a short packet instead. So all of the packets in the whole design get replaced. Let's say for another test, we just want to replace the data packet in agent 0 with a short packet, and we want to replace the agent 1 driver with the new version of the driver. So you can do an instance-based override as well. The first one was type-based, now this one's instance-based. So here I have a set inst override syntax, short packet get type, and then you give it a hierarchical path. You can use stars. So I'm going to override data packet in my agent dot star with short packet. And then on the bottom, again, you probably can't see it if you're in the back. For a driver, you can say my driver : type ID, set inst override, my V1 version of the driver, get type, and then a hierarchical path. And then what would happen is the agent 0 packet would only be modified, and the agent 1 driver would be the only one modified during building of the test bench. Okay, so that's the factory and the configuration mechanism. And there's just a couple more things. One of them is messaging. So messaging is a standard way. You know, when you have a very large environment, it's important to have a structured way of reporting errors and warnings and informational messages. You want to be able to categorize the messages based on severity. So some things are fatal, some are warnings, some are info. You can actually take action based on this. So if you have a fatal error, it will end the simulation right away. Or you can say, if I have 4 errors in the design, I want to stop at that point. Another nice thing you can do, for example, summarize the number of messages reported. So the requirements for UVM were to have a uniform output format and an ability to turn messages on and off without having to recompile everything. You have control over the format, the actions, and the filtering, and you want to also have a minimal performance overhead, because messages, you know, displaying messages can be a huge performance burden. So the messaging facility that's built into UVM, it's aware. There's some advantages over dollar display. Number one, it automatically captures information that you might want to know. For example, where it is in the scope of the test bench. So traditionally, with a Verilab design, you could use %m, and it would say, you know, I'm in test.top.dut.block1.memory. That's not possible with dynamic simulation. So when you use UVM info or the UVM messaging, it does know where it is in the scope of the test bench. And then you have the ability to filter things based on where you are in the test bench, the verbosity, and even the time. So here's an example. I have UVM info. You give it a tag, packet. The message itself, this is the string that you really want to display, and then a verbosity. And this is what you get, all this extra data. It tells you what type of message it was, the severity. It can print the file name, the exact file that it came from, and the line number, the time, the simulation time when that occurred, the scope, the little tag, and then the message body. So you get all that just for one small tick to find. Yes, did you have a question?
Is there a way to add more verbosities? There's only 5, right, defined?
The verbosity is actually just a number.
Okay, but it's like low, it's none
Right.
high.
Yeah, so 0, 1, 0, I think high is like 400 or something, and then you could do 401.
Okay.
So you could just do slightly higher verbosity. It's just a number.
Okay.
And you can change it as you like. So simple messaging, use tick UVM underscore error, fatal, warning, or info, and then you give it the string message and the verbosity. Verbosity is only valid for UVM info. So that's that. Callbacks. Callbacks are another way of altering the behavior to affect an existing component from the outside. John talked about the mid-do and pre-do and post-randomize. These are some built-in callbacks into UVM. When you use callbacks, that you are required to predict where these changes are going to happen, and you create the hooks yourself. The nice thing about callbacks is you don't have to use any inheritance, and you can combine multiple callbacks together. So you can actually have more than one change in behavior or more than one callback for a specific hook. I'm not going to go through this example. It's in your handout. This is how you would use them. You have a developer code. The developer sets it up and specifies so he extends from UVM callback, he registers it, he calls the callback at the appropriate time inside. This would be the driver has some sort of callback. And then you can specify a type def. Then what happens on the user side is the user extends from that type and creates the function that the driver is going to call. And then you have to create the callback in your test or your test bench, and you attach it to the specific instant or type wide. You can modify all drivers here or just a specific driver. The implementations are usually created by the test writer, and then they apply it for a specific component or a specific test. But there is one cool callback that I like to show people, and that's the message, the UVM report catcher callback. So it's a built-in callback. So you can actually capture messages. So if you've injected an error for a special test, you can capture the error and turn it into an informational message because you know that in this case you wanted to find an error, a scoreboard error or something. So here we have an example where we extend from UVM report catcher. You get the severity of the error message, so any error message that's called, that gives you an error and the ID, this is that tag is my ID. It modifies the severity to be UVM info, so it'll be printed as an informational message instead of an error. And then it'll increment the count there, and then you can either throw it back and it can keep getting manipulated, or you can say that's it, I'm going to catch it and it's not going to do any more processing. So this example would demote any message, any error message with the tag my ID to be an informational message. So here I might have in my test bench, I have to create the message catcher and I have to add it to the report callback. And the first one would be demoted, and then you can actually disable these callbacks at some point in time. So you can disable it, callback mode 0, and then the next time you get that error message, it actually will fail. Okay, I have one more thing I want to cover, command line processor. So this is a vendor-independent way of adding, modifying the behavior of UVM using command line arguments. This is above the capability of $value, $+ args. So there are some basic things that you can do. You can get arguments, you can get plus arguments, you can get argument matches, and you can get all the UVM args. You can also do stuff like get the name of the tool and the version. But the ones that are really cool are these UVM aware command line arguments. You're already familiar most likely with UVM verbosity and UVM test name. But then there's other things you can do, like you can do a set config int from the command line. So for a special test, if you only want to run 5 packets, you can actually do an override of a value from the command line. You can do set config int, set config string, UVM set severity. You can do a type override from the command line, and you can change severity from the command line. All of these you can do hierarchically, so you can change the severity or the verbosity for a specific component deep inside the design. So here, for example, I used UVM set config int. You give it a field. Comp stands for what? Component. So I have UVM set config int star coverage enabled to 1. So I'm enabling coverage throughout the whole test bench. And then I also can do a hierarchical spot where I want to enable coverage. So here I've set the configuration for a specific bus monitor. I want to enable the coverage there. If you have star, you have to put quotes around it. Otherwise, they're not required. Use star if wildcards are used. The next one is you can modify the severity again for a specific component in the design. So you can change the severity for some place in the instance hierarchy, the ID tag, the UVM error, which would be the current severity and the new severity. You can change the actions. You can do instance override and type override as well. So I tried these, they work, they're very cool. Note, this only works for string-based factory, so parameterized types can't be overwritten from the command line. Here's an example of the command line processor. I'm not going to cover this slide. This is how you can use the tool, get tool name and get arguments and things like that. It should be in your handout there. And then I just have a summary slide. So I introduced you to some of the techniques for customizing your test bench or your verification environment. We have the configuration mechanism to allow you to configure components and data objects from higher levels of hierarchy. We have the factory to override the values of things, of data objects and components for specific tests. We have messaging, we have callbacks, and we have this command line processor. So these utilities are part of UVM to make reuse possible.
So register modeling in UVM. The register modeling is something which I guess we all do as part of verification. And it was one of the big things when we came to UVM as to how do we get it into a standard and all agree to what the standard register mechanism should be. So it's a fairly large, chunky bit of code, but it's actually really important. Okay. So there's also various elephants throughout this presentation, and there's no prizes for guessing what elephants are or where they are. We can discuss them as and when they come up. And if also there's meetings to the presentations after lunch, so give you a reason to come back after lunch. And we'll get finished before lunch so that you can enjoy that as well. Alright, so we're going to split the presentation into 2 sections. The first section is going to be about the register package itself, the structure of what it looks like and how that is constructed to be register files, address maps, etc. And then the second part is going to be about using it with the DUT. Right? How do you integrate it? How do you write those sequences which you guys have been talking about this morning, and how do you use it with just general system Verilab code? Okay. So let's do the first part first. So the register model hierarchy is from top down. You have a block, which is your entire view of what's going on. And within that block, you can have sub-blocks, you can have register files, and within those register files, you can have other register files, and you'll have registers, right? And then the register itself will have the bits, the fields in there which you want to control. Some of them may be 4 bits, some might be 2 bits, some may be 32 bits, etc. So that's the lowest level granularity we go down to. Okay? And adjacent to that, we also have memories, right? And you can see the 0 to infinity here. So you can have 0 to any number of them. Obviously that's to map to what your actual register space looked like for your design, right? You're not just going to make up a random register space. Now, System Verilog has some fantastic features, and it allows us to develop introspection on top of the language which is there, right? So we've got System Verilog at the bottom, we've got UVM base class library, and we can use the functionality from both of them, and then we have the register layer, the register abstraction layer on top of the UVM. And then within that register layer, we can add in register-specific introspection. What do we mean by introspection? It's a querying mechanism. So I can go and from within the register file, I can say, get the block. Who is the block that you want to access? And so then that register file will go and run that function. And so forth with the other components in the system, other objects there. Right? And this is really useful so that we can know not just who get parent and get child are, or get child is inherent in system default system level, but you can use get parent and you can find out where the registers belong or where the fields belong within the entire structure. The other interesting ones that we like to point out are things like get offset, so you can find out where in the particular register map the actual register lives. So you can have various registers with various offsets, okay? And you can access them all introspectively. So what does it look like from a user perspective? Right. So we've talked to the blue boxes are what you get with the UVM pattern, with the UVM base class. Okay. So this is a bit of a UML. So the arrows are is a derived from, and the diamonds are has it has one of those things. Right. And you can read about more UML on the web, whatever you want to do. So they're all derived from UVM object up in the corner here. Right? And then we can go through, and the user code is the white code. Now, we say here, the first elephant is it's generated. So we expect that you will write your registers in whatever abstract view you want, right? And then you'll have some mechanism that will generate for you the system Verilog UVM structure of what that abstract language, web page, whatever it looks like. And that generated UVM code, you'll have a block which will derive from the register block. You'll have some registers which will derive from the register class. And you'll have some file which will derive from register file, and you'll have the fields which will be inside of MyReg. Okay? There are lots of tools and in-house ways of generating the UVM register API. So that's the first elephant. Okay. And the UVM standardized the system Verilog part of it. They didn't go off and do some other language or mechanism for implementing the registers. Okay. So we're into how does it look? So we pick up our data sheet and we go through our spec, and somewhere in the spec there'll be the software view. There'll be this is the view. If I was a software engineer, how I would access the device. So we're away from bus transactions, we're away from little low-level bit interactions, and we're up at the programmer's view. We need to be able to model that entire programmer's view for verification. we need to be able to define where all of those registers live, how they're accessed, whether there's memories in the system, whether there's arrays in the system, etc. Arrays are here. And so this is how we do it. So no guessing for R stands for register and F stands for field. Easier on the PowerPoint. So we have our registers, and within our registers we'll have certain fields. And then we could have arrays, and this is the same register stored in an array 0 through to 255 or 1 through 256. Right? So that's the replication. And then you can have multiple register files, which is a collection of registers, and you can have these again in various implementations there, RF0, RF1, etc. And down at the bottom here, I'm showing an example of a memory. You can probably see that almost at the back. So here comes the next elephant. How do we actually model an entire memory? And some of you guys have been doing it from your own verification. You've used register packages in the past. You may have used sparse memories, or you may have actually instantiated the entire memory. So we try not to do that. We can discuss that a little bit. All right. So let's take these one at a time and look at how they're actually constructed. Okay. So for all of these Fs, all of these register fields, we have a class called UVM reg fields. Not a very surprising name. Within here, we'll have the name of the field, the bit position as to where it lives, and various access policies. You can define the access policies, as in is it a write one, clear, is it a read only, is it a read write, etc. And then we have the basic read write functionality. Okay. So what do I do when I do a write of that register onto the interface? What do I do when I do a read of that register onto the interface, etc. The access policies is another elephant. Everyone in the world, I think last year we were talking with one of the register EDA companies, and they were telling us that there's so many, various thousands of ways that people have decided that they're going to have access to the registers, not just a dozen. But, they'll have quirky accesses, etc. So we have some defined in UVM, and we can talk about later other ways that you can manipulate the access policies. All right. Okay. Now for all the R's, we have a UVM reg. So we'll create our UVM reg, and within there we'll have all of our fields. So our generator, our code will come up, and it will say that for R1 reg, I want F1, F2, and F3. Now, of course, we want to try and make everything not namespace collision. So we want to try and make these more than generic terms, right? So that's just a bit of a caveat. But fundamentally, what we're looking at is capturing the field information for a single role in your programmer's view within a register. Okay. And each register has its own address, right? So you don't need to access just a single field in there. We're abstracting out. So we're going to be able to abstract from the fields into accessing field registers. Okay. In most applications, you actually access the register. You won't access a single field. You'll be wanting to write to an entire register space with certain values for the fields inside of it. Okay. So the majority of your verification will be done using the register space. Alright. So let's move from registers onto register files. So really here what we have is a collection of registers. Okay. So in here we have RF0 and RF1 are our two register files. And within RF0 and RF1, well, we can have R0 and R1. So these are registers, not fields. So again, then we'll come and we'll generate in here this API for having the register files and what goes into those register files. So I think we just talked about that one. Right. So here comes one of our first elephants. So we have the definition of a memory, but how does this really look like, right? So if this goes from 0 to some huge number, 4 gig, 2 gig, whatever, then we don't want to represent that entire memory inside of a verification. So what we have is we have the class container, which contains all the information about that memory, but not the memory itself. Okay, I think that's quite an important thing to point out. Right? So the attributes which belong to the UVM mem object here is how big is it and where does it live, and then the access policies as to what it can do, right? But it is not actually a 4 gig memory sitting in your verification environment. All right. So here we go into a bit bigger system, right? So we now have a block. So the block is the entire overview as to what's in the system. Okay. So here we have R1, and we can see that R1 is this entire register here. So this has got certain fields in it. Now I didn't instantiate field 1, field 2, field 3. I instantiated the register which has already got the fields inside of it. Okay. And the nice one, or the interesting one, is the arrays. So we can actually just say that there's this particular register and it's splatted out 256 times. So we can start doing much higher levels of abstraction. One thing that I didn't do at the beginning of the talk was explain why we want to do register verification. I kind of think that at this stage everyone has been through some pain of doing register verification, right? So these kind of problems are really about how do we address them, right? So how do we model it most efficiently? And the same for the register file. We can have in here an array of how that register files are spat out, right? So this block is the entire system that we want to view. Alright, so here we go. So we put that then into the system, and you can then have multiple subsystems within a block, right? So we had before a block, and these guys are also blocks, and we can then instantiate blocks within blocks. So you can start building up the various register maps, right? So you'll have DUT block level verification down here, and then that block level verification becomes a subsystem verification, in this case the UART, and then that UART goes into the entire system, and that then becomes your chip level verification. So these blocks can be reused up and down that level of verification. Okay, so that's why we have blocks within blocks. Okay. All right. So the basic APIs to access this information is defined here. We have the introspection API, and then we have the read and write mechanisms. Right. And we'll show these read and write mechanisms when we do the DUT integration, when we actually use this with the DUT as to how it goes hand in hand with verification, right? So you can access, as we said before, you can access a field, read and write to a field, you can read and write to the register that that field is contained within, or you could access an entire register file, or you could do an entire memory read or write here. So this is going around all the fields inside of a register, inside of a particular register file. So there's various granularities that you can access these particular register fields inside. Alright, so then it comes to, well, that's fine, but what I have is I have various devices, and all of these devices want to manipulate or see the register information slightly differently. And so for that concept, we've implemented maps. So we have a variety of register maps. There is one default map, which is within the block. And the block has an access to that map, which is the default view of that particular register space. Okay. Now what happens if I have an APB bus, an HB bus, and a Wishbone bus? And these guys see the same register information slightly differently. So they can have independent maps, right, rather than having completely different independent register block space. Right? We don't want to create lots and lots and lots of register blocks. We can manipulate that information using a map. So here's what the map looks like. We can instantiate the map within the block, and then we can have down here, when I perform, and you probably can't see this at the back, when I do block.x register.write, I can specify which map that particular X register is going to get updated with. Right? So X is in here, it belongs to both HB map and wishbone map. I think actually this comes back to one of the questions before, was can the same register live in various locations? Right? Various perspectives, I guess, is the way you can put it. Right? So here we're accessing X, and we're specifying the access of X to be using the wishbone. Alright. Okay, and then coming back to one of the other questions at the beginning was, well, how does this actually map onto the width of the register space itself? So if I access a register, r1.read, then I access the full, in this case, 32-bit register. If I access f5.read, then because f5 is the only field in that register, I'll access all of that field within that register. I'll access all 32. If I try and access f1, it goes all the way from some point in the 31st bit to some point in the middle. Now, I can't actually access the independent words. So what happens is that when I call the access for F1, I get the whole data structure. Right? So that's that difference between half word, word, and full word. Okay, so moving on to the access granularity, if your protocol has support for byte enabling, then you can leverage that to be able to actually split up the access for F1 to be that particular section on the address. Right? Otherwise, by default, there's no byte enabling. Okay? And that's the same for F2, is that you can specify that it starts at one location and then the next address location is on the other word. Right? So this comes down to dependencies within the protocol which your registers will be applied on top of. Right? And the UVM has no concept of protocol. It has no idea what you're going to design. Okay? And then the various register reads and writes can happen and so forth. Okay, obviously all ones is all byte writes. Alright. Another big elephant is coverage, and the coverage topic is actually, I'm going to go through this briefly because it's on the Verilab presentation straight after lunch. So that gives you a reason to come back after lunch. Right? So they actually show how they've enabled and used the coverage for their product application. All right? The fundamental principle that we can take away just now is that the coverage is there and it's enabled for a variety of different abstraction levels, as I just clicked through here. You can do it for bits, you can do it for addresses, and you can do it for fields within the register model itself. By default, it's not on. I always equate bit level coverage to toggle coverage. It's nice to know that you've done every bit, but it's painful for simulation performance. So this is the fun part. How do I actually use this with my DUT? Right. So there's a bunch of steps, and there's a bunch of primers, and as I said, there's the UVM User's Guide Manual as well. Okay. Many of these steps are covered again after lunch, so I have a very brief overview as to what's going on here. Fundamentally, you want to plan ahead. You want to go ahead and see what's going on. How do I reuse this from a verification perspective? Do I just want to verify my block, or do I want to verify my block with some other block or within some SIP system, or do I want to change from APB to AXI to Wishbone? all these questions need to be addressed up front so as that you know that you want to use something which is highly reusable. Okay? And that's the fundamentals behind the register mechanism here. So the register model doesn't really know about all the bus interaction, etc. Right. So the register model itself is built, and then we generally recommend that you do a lock. Okay. So the lock means that all structural information should have happened before that point in time. So you can't add to registers dynamically. Well, you could, but it'll probably break everything, which is why we lock it. Right? You don't want to have a block of register space and then halfway through your simulation add a register. That's just not practical. Software can't do that. Real hardware can't do that. Okay. The mechanism here is also shown after lunch is to actually have an adapter, right? So we have to have a mechanism that says this is the register information and this is the bus information. How do these two communicate, right? And that's the mechanism where we use here is to actually say construct the adapter, and then the bus level sequencer and sequences that the guys earlier on today talked about, you can use that infrastructure, that driver sequencer sequence interaction. Okay. What we need to get to is we need to get access in and out of the bus. Right. So we have built-in adapters in UVM, and you can then, for your particular protocol, however it works, maybe it's some derivative, some internal protocol, however it operates, you can define the mappings between what goes on the bus and to what the objects, the registers and the fields within those registers, how they're used. Right? So in this case here we're using ITC, and ITC has got a variety of addresses and M&S modes and transaction types, etc. And all of those need to be mapped into the register space, okay, into the fields of the register. And then the reverse is true for when you go from the bus to the register, right? So it keeps the register away from the bus interface. Well, the only part which is communicating with the bus is through the adapter. Okay. So then there's two modes of updating the register model. One is the implicit monitoring and one is explicit monitoring. And the implicit monitoring means that the register model itself, when I do block x.write, it will update with that particular write, whatever I've done. And in that mode, we assume that the other masters or other devices on the system will not see that particular register read or write happening. Therefore, the model itself will update it. It will update with its own information. Okay, and then we call this implicit. This is off by default. So by default, what happens is, and again, this is explained straight after lunch. By default, what happens is explicit monitoring, where we expect that other masters in the system will see the register bus operations, and then they can post that information back to the register model to say, I saw this happen, here's the values that you should be using now. And that way we can keep the model up to sync with whatever's happening on the bus interface. All right? So come back after lunch, once we're there. The accesses that we do from the register down to the bus level information is the same as what we've been doing all day today. It's through the sequence item and down to the driver. And this, for instance, the resetting the model is something which is built into the UVM register code, but the way to use that is the same as what you've been seeing all morning, right? So inside the model there is a reset function, and all that basically does is it puts your model back to the original state of time zero. There are resets. Most registers have a reset default value, and it will initiate the reset for that particular model. However, the structure here, the test, the phase, the function phase, as Tom pointed out, you could put this in in the environment or the test case, and then the raising and the dropping of objections. That's our normal system Verilab code. As John pointed out earlier, you know, it's probably blowing your brain. So this is just icing on the cake that you should remember this from earlier today. Okay. There are predefined sequences, so we don't just let you go off and do whatever you want. We try and give you some help. We know that accessing all the bits, bit bashing, is kind of what everyone wants to do. We know that resetting the device is something which is useful to do, and there's a whole bunch of other ones. I think there's 6 or 7 that we give. And so you can just instantiate one of those predefined sequences and then use them inside of your test. So this little smoke test here, all I'm doing is instantiating a predefined sequence, and then I'm telling it to go off and start. The one thing that we do is you have to set the register model that sequence should use. So the whole point is we have one register model, everyone accesses it, so they update it, right? And the rest of this infrastructure is, as stated, you should remember this from about 50, 60 slides ago. Right. Okay. So that's some predefined stuff, and then you want to go beyond the predefined and actually use your own read and write mechanisms. So we've talked about this, I think, at length. You can do read or write on fields, on memories, on registers, on register file, on those various access points in the system. The one interesting thing which we did was we made sure that any access is done not using strings. Right. And this is important because a string the compilers can't check, so you could easily miss out a bracket or miss out a 4, and the simulation will run and for whatever 2 days, and then you'll try and do a check at the end that all the registers are correct, and you'll get an error because you've typed something badly. Right. So having this type of compile checking is very important and very efficient. You'll get a cross-module reference error or something like that if it doesn't exist. All right. And then you can use that information, these reads and writes, to create your own sequences. So again, as stated previously in the presentations, you write your sequence, you have all your sequence code, your bodies, etc. And then within here, you specify, using just plain vanilla system Verilog, what functionality you want to execute. Right? So you can have case blocks, for loops, while, whatever funky system Verilog code you want to write, fork join, all that good stuff, and then you just use the API, the write and read APIs. Okay? So we really are trying to keep it something which is manageable and usable. Right? You don't have to learn anything that's overly complicated. Right? And then to use that, you just use normal UVM system Verilog code, which has already been shown. The one thing you have to remember is there's only one reg model, so you use a reg model assignment, a handle assignment, and then you start that register. And you start it on no sequence, and it goes off and uses the register sequencer by default. So there's some implicit, it knows that there's a sequencer there to use. So this is the million-foot overview of the registers. There's some more details after lunch. The Verilab folks have got a presentation, and one of their sections is how they used various techniques and used coverage and used monitoring inside of there. And then there's multiple different subtopics. Right? So this itself, as Doulos pointed out, could have been like a 3-day part of a 5-day or 10-day UVM training. Right? So doing it in a 45-minute snapshot is bound to eat into your lunch, which you can go and take now.
So, as Tom mentioned, the afternoon is strictly focused on user experiences, and I get the pleasure of starting us off with getting started with UVM. So to set the stage a little bit, why I've entitled it that, to give you a little bit about my background, I did verification for a while, and then when I joined Verilab last year, my first role with the clients as a consultant was to build a UVM test bench. So this was going to be my first opportunity to work with UVM. So what I would like to share with you during this presentation
some of what I've learned over the past few months ramping up, hopefully maybe some best practices and some tips of what we've done in our environment. So we're going to look at the test bench architecture that I'm working with, a little bit about how we're using the configuration database, connecting the scoreboard, and then I'll focus a little bit on the register model, specifically the UVM reg predictor and then coverage. So first, let's take a look at the test bench architecture. So when I started this, my task was to build a UVM test bench for the DUT, which is essentially a pipe. And by pipe, I mean the data comes in, is transformed by various blocks in this pipe, and then is output, that transformed data is output via the same interface. So I needed to build a test bench around one of the blocks in this pipe that would be reusable among various blocks in this pipe. So there are three major UVM components in this test bench. The first active component, and by active, as we heard this morning, I mean as a monitor, driver, and a sequencer, is my AHB agent. The AHB agent in this environment is strictly responsible for driving the register read and write accesses. The second component, active component, is what I'm calling a pipe input agent. So it's driving data and stimulus through the data path of this pipe. And then I have a passive component, which is reusing that input agent, but I'm only instantiating the monitor in this case because it's passive. So first I had to create the AHB portion. And once that was done, I focused my attention to the input agent. And it was here where I first really needed to understand how the configuration database works. So I just want to walk through an example of that. So as I mentioned, I'm reusing the monitor and my input and output. And I'm instantiating the interface twice. So I needed to figure out how do I get the monitor without hacking the code to select the right interface. So that's the example I want to walk through. So as we saw this morning, the first thing you do for your interface is instantiate in the top level. And at this point, I'm just kind of focusing on the input. So I've instantiated my interface, and now I'm using the configuration database. I'm calling the set function to put that instance of the interface into the database. So let's look at the set function. It has a context, instance name, field name, and value. And Kathleen went over this earlier, but just to kind of cement what she went over, in the top level, I'm using UVM root get, which is essentially just getting my top level. I'm using the glob she mentioned earlier, which star, to make it globally available. And then I have a field name, in this case DUT_interface, which I like to think of as just a label for whatever I'm putting into the database. And the value I'm putting in is this virtual interface. So when I retrieve it, I can refer to that label or name, DUT interface. So on my monitor, I'm now using the get function to retrieve it from the database. So the get function, similar to the set, has the context, instance name, field name, and value. So I'm getting that virtual interface based on the label DUT interface, and the value that's actually in my monitor, the virtual interface, is being assigned that value that it's pulling from the database. Also, I want to point out the second field, instance name, you notice is just quotes. It's an empty string. You can do this because the instance name is relative to your context. So since my context in this case is the monitor itself, I can leave the instance name blank. Now for the simplicity of the slide, I just showed the get function, but I want to point out here, and we saw this morning as well, that it's a better method to encapsulate your call to the configuration database in an if statement and invert it in case you don't get the interface, it's a typo or you use the wrong type, you follow it by UVM fatal UVM error. Kathleen mentioned earlier that the recommendation is UVM error. I actually use UVM Fatal because I like the simulation to stop right away. The first time I did this, I didn't follow it by a fatal error, and I spent a lot of time trying to figure out why I wasn't getting data traffic. With this, the simulation stops right away. I have the no VIF tag, and I instantly know what the problem is. I don't have my virtual interface, and now I can spend time debugging why I didn't get the interface as opposed to trying to figure out what else could possibly be wrong here. So now I have the input done, and now I need to instantiate the monitor for the output in a passive mode. So once again, in my top level, I've added a second interface, and I've renamed them to indicate, this is the input interface and the output interface. And now I've put them both in the configuration database with a distinct label for the input and the output. And like I said, the challenge or the problem I'm trying to solve is, well, now I have these two instances in my database. How do I get the monitor, whether it's the input monitor or the output monitor, to select the appropriate one? So what we did in the monitor, I've added a string, monitor interface, and I'm going to use that string to get the value from the database and then assign it to the virtual interface that I have instantiated. So in my environment, I first, if you remember, the labels I use, and I'll actually go back a slide. The labels I use for my interface is input DUT interface and output DUT interface. I'm going to reference again here. So now I'm using those labels as the value. So I'm going to get that value, I'm using set, so I'm putting into the database, and I'm associating this label monitor interface with the previous label, which is now used as a value for the input, and I'm also doing the same for the output. Also note here, I'm explicitly doing a path, so I'm making this available only to the input monitor, and this one only available for the output monitor. So now in my monitor, the first call to the database is a get, and I'm going to get the value that has the label monitor interface and assign it to the string monitor interface I have in my monitor. Once that's done, I can then use that value that's in monitor interface and assign it to my actual virtual interface. So I said the purpose of this is so you don't have to figure out a way to hack the monitor code to say, okay, for this I want it to be input and for this I want it to be output. You're using the configuration database to push and pull information. One more point I would like to bring out about this. In my top level, as I mentioned, I use star to make it globally available. You want to minimize doing this as much as possible because it could have a performance impact as well as a debug impact. So let's say, for example, you have 200 items in your database and you need to debug just one. Well, now you print your database and you've printed out every resource or every configuration item you have, and you're only really interested in one line. So a better method would be to specify some type of path, even if you're using, star dot whatever to limit this just to a monitor or maybe just for a driver, so you can have ease of debug when you're trying to go through the printout. Now that was just one way of doing it. There's the good thing about UVM is you can adapt it to your environment however you need to. It's a library that you can utilize for your application. So what I've just shown is one way of doing this, and I'm going to walk through a second example using the resource database. The difference between the configuration database and the resource database. The configuration database, as Kathleen mentioned earlier, is actually built upon the resource database, so you can use them in conjunction with each other. So if you put something into the database using UVM config DB, you can retrieve it using UVM resource DB. Now, when you are adding something that the hierarchical context is important, let's say you need to enable every coverage bit in every agent, then you want to use the configuration database. It was built specifically for a hierarchical context. If hierarchy doesn't matter, you just need to put an element in the database and then retrieve it wherever, then the resource database is what you would want to use. So as an example, using the same interface, I want to walk through the resource database. So first, we let the interface name itself. So my actual interface, I have a string interface name, and I'm just using %m to assign it its name. And then I'm going to put the interfaces in an interface registry. So here I'm using the set function with UVM resource DB. I'm calling it interface registry. The second field, I'm giving it that name that I've put in the interface, and the final field is the interface. So let's take a closer look at the set function. So it has a scope, a name, and a value, and then a UVM object assessor, which is defaulted to null. So once again, in my set, the scope here is interface registry. So you're just basically giving it a string name to start out with as a lookup for everything you're putting in this registry. That name could be whatever you want, interface registry, coverage enabled, things like that. The second value is the name, so I'm actually using that interface name, and then finally the value. So I'm putting the input interface in there, as well as I put the output interface there. Now in my monitor, instead of using the configuration database, I'm using the read by name function of the resource database. So the read by name, similar to the set, has the scope, name, and value. So once again, the scope is interface registry. I'm still using the monitor interface string that I have, and then the value is the virtual interface in the monitor. So in my environment, I'm still using monitor interface to get whether it's input or output. So I'm using the configuration database, like I mentioned, in conjunction with the resource database to get the interface. Now, this is an example. As a best practice, you want to use the configuration database for your interfaces because more often than not, it's important to have a hierarchical context. So now I have my test bench up and working. The data is flowing through from input to output. Now I need to do some checking. So let's take a look at the scoreboard. So as we saw earlier, you can have the monitors have an analysis port, or you can declare an analysis port that broadcasts data to any subscriber. And this subscriber, and the subscriber in this case is the scoreboard. So when I developed this, I'm like, hey, in my application, what's the easiest way to connect the scoreboard to the analysis ports in the monitor? So in my monitor, I have an analysis port, items collected port, that's parameterized with my UVM sequence item, a data packet in this case. I also have two data collected and a data clone that are of type data packet. So I'm actually cloning the data first and then writing that data to my analysis port. So the actual code for that is I'm cloning data collected here, and then I'm casting it to data clone, and then I'm writing that clone to the analysis ports with the write function. Now the reason you would want to do this is when you write an object to the analysis port, you're not creating a new object, so that object is sent to the subscriber. So if that data that you're collecting changes, it's also changing in your scoreboard or coverage object. So I guess as another example, in our environment, the data I was collecting had 4 queues. And so I would add data to the queue, write to the analysis port. Well, I didn't want the queues to continue to grow for each transaction, so I would delete the queue, which would then obviously delete the data that my scoreboard needed to do comparing. So I cloned it first so it has its own copy, and then I can analyze it from there. Now, by doing this, I'm making a certain assumption that the subscriber itself is not going to change that data packet. So let's say, and if we saw this morning, the monitor, the analysis port, it just broadcasts, and whoever needs it can pick it up. So let's say you have a scoreboard, a coverage object, and 2 other subscribers that are connected to this analysis port. They're all getting that cloned object. So if any of those subscribers change the data, well, now it's changed in each subscriber. So if you have a case where you're connecting to multiple subscribers and it's possible that data could change, then you would want to wait and clone your data in each of those subscribers immediately when you get that packet, so it has its own unique copy. So now in my scoreboard, instead of using an analysis port, I found it easier for our application to use the UVM TLM analysis FIFOs for 2 reasons. One, it already implements a queue as a FIFO, so it can collect the packets that I'm writing to the analysis port. Secondly, it already implements the write function, so that's something I wouldn't have to do. So I have 2 of these instantiated, one for the input, one for the output, and they're both parameterized to my UVM sequence item type again. Now I have various watcher tasks to watch and wait to see when that data is collected. In this example, I'm waiting at the positive edge of each clock, and then I'm checking to see if there's data in the FIFO. And the reason I point this out is, notice here that I've used items input packets collected.use. The first time I wrote this, I used .size, and it was constantly returning 0. And so I looked in documentation, and finally I went to the source code and realized that for the FIFOs, .size returns the capacity of the FIFO. And if it's unbounded, as it is in this case, then it's always returning 0. So what was implemented was a used function that returns what you would think of as size. So the reason I'm pointing this out is to say, if you're working on your test bench and you're stuck, there's the user's guide that's in the installation. There's the reference manual. It's available in PDF and HTML. I like the HTML because you can easily search. You can just type in the function name and it'll pop up a list where it's available, and look at the comments, look at, sometimes you actually go to the source code. You really can't find what you're looking there or don't understand it. Go to the source code itself. It's open source for a reason. You can read through it, understand what's going on, run your simulator and step through the code to see the transition so you can get a better idea of how everything is working. So it can save you a lot of debug time if you, like I said, utilize the documentation and also go to the source code. And finally, just for completeness, I want to show the actual connection. We saw the connect function a lot this morning. So in my environment, I'm connecting the items collected port that's in my input monitor to the analysis export port in my FIFO in the scoreboard, and the same for the output. Now finally, I also want to mention, on 2 slides ago I talked about this .use, and I'm checking at the positive edge of each clock. Well, this is really not a good thing to do, to refer to your clock or any top-level item in your scoreboard, because it makes it less reusable. So a better method would have been to use the .get function that John talked about this morning in his TLM section. Get is blocking, so it's sitting there and is waiting for a packet. Once it gets that packet, now I can call any task I need to, such as compare. If, let's say, you need to collect several packets before you move on, then peek is also blocking. You may peek, and once you have several packets, then you move on. So once again, to really fully understand what's going on, take a look at the source code and go through it, and you can easily pull out what you need. Okay, so now my test bench is up and working. I'm doing checking through the pipe interface. Now I need to focus my attention again to the AHB portion, which is during the register read and write accesses, and I need to implement a register model. And Adiel talked about this earlier, how most of the code is generated. Fortunately, I didn't have that luxury. The client I'm working with didn't have a tool to generate it, so I actually had to create my register model by hand. So, which I don't recommend, is actually quite tedious. So the AHB bus is pipelined, and the problem I had when I initially started was my write accesses were happening fine. I would write the data, I would see it on the bus, then I would do a read access, and I was constantly getting back 0. So I was trying to debug the register model to figure out why I wasn't getting the read data accurately. So as mentioned earlier, the register model is connected to an adapter, which is connected to the sequencer. So the adapter implements, you have to implement two functions, reg to bus, which takes the object the register model creates and converts it into your sequence item type, in this case an AHB sequence item. The second function is bus to reg, which takes the packet from the bus, or the data from the bus, checks to make sure it's the right type, and then converts it into that object that the register model understands. So looking at the AHB protocol for read access has address phase and data phase. And as I mentioned, for the read access, I was getting 0 back at the positive edge of clock when I would do the read access. So my first thought, well, the register model should know about your protocol. The adapter doesn't know about your protocol. So what am I missing here? So once again, I turned to the documentation and started reading and found out about the UVM reg predictor to do explicit prediction. So the predictor is getting information from the monitor about what's happening on the bus, and then it updates your register model with that read or write information. Say, hey, I observed this write, or I observed this read. So now the predictor is connected to your monitor, the adapter, and the register model, so it can update the register model with the observed information that's coming from the monitor, and it's also connected to the adapter, so the converting of the objects can happen appropriately. So to do this in your build phase, you create the predictor with the UVM sequence item type. In my case, it was an AHB transfer. In the connect phase, you set the predictor map to the register model map. You set the predictor adapter to the register adapter, and then finally you connect the predictor to the monitor. So let's take a look at how that actually looks in the code. So I've declared my reg predictor, which is the type UVM reg predictor, and I've parameterized it with AHB transfer. Now in my create, I created also in the build phase using the factory like we saw earlier. Now in the connect phase, I'm connecting the map in the predictor to my register map. I'm also connecting the adapter to the adapter that I didn't show the instantiation here, but the instantiation of my register adapter, in this case, reg to HB master. And then finally, once again, I'm calling the connect function. I'm connecting the analysis ports in the monitor to the analysis ports in the register predictor. Now here, I need to set auto predict to 0 for explicit prediction. So let's talk a little bit about the different types of prediction again. What I was doing at first was implicit prediction, where I would just write and read the data, and the model should be updated based on that write or read. As I mentioned, I wasn't getting the read data back appropriately. The problem there was I wasn't capturing the packets and sending it back as a response in my driver. So that was important for me to do based on this protocol. So instead of just get next item and item done, I also needed to do a put response. And then your adapter also needs to set the bit, provides a response to wait for that response to happen. So once I did that, I could easily use the implicit prediction, and you would set auto predict to 1, and my model is updated based on that write or read. Now, it's not, in this case, it's not getting any information from the monitor, so it's basically the data in the model is what it thinks it should be. Now, with explicit prediction, using the reg predictor, like I said, you set auto predict to 0, and it's getting the data from the monitor, so the data in your register model is always updated what should actually be in your RTL. Finally, there's also passive prediction, where you're still using the UVM reg predictor in an explicit mode, but there is no sequencer in this case, so you cannot do writes or reads from this register model. So what my environment looks like now is for my stimulus and the sequences, I'm using implicit prediction with that register model, so I'm only doing the writes and the reads. I'm not doing any checking. For the scoreboard side, I'm using a second instance of the register model, and I'm doing checking there. So it observes the writes or reads, and if the read is incorrect, it lets me know. Now, I mentioned checking. Checking is not turned on by default. All of your registers are checkable, but to actually use it as a scoreboard and check that your read data is correct, you need to, instead of using the read function to read the register, you need to use MITRE. MITRE has a field where you can set UVM check, and it checks whether the data is correct. Now that's true for UVM 1.1. And UVM 1.1a now, which is out, they've added a set check on read that you can set to 1, and that basically combines the functionality of your read function and your MITRE function. So with UVM 1.1a, I can set check on read, use the read function, which feels more natural because you want to do a write and a read, and then it checks to see if the data that is read back from the RTL matches what is in your register model. Okay, so now I have my register model working. I'm getting the data updated correctly. Well, now I need to do some coverage. So now I've added a coverage element to my environment for HB. Like I said, the predictor's working, the register model is working. I now just want to use the built-in features of the register model to make sure I'm accessing all of my registers. So in my register model, in the constructor, I've called build coverage, and I've used UVM coverall. There are several different enums you can use to determine what kind of coverage you want. So both in my UVM reg and my UVM reg block, I've turned coverage on this way. Now when I did this and ran a simulation, I got these warnings over and over again: include coverage not located. Did you mean this? Did you mean that? For every instance of register. Fortunately, I only had like maybe 25 registers, but it was still annoying to see this long list of messages because it doesn't have any kind of UVM warning tag, so I didn't know where this was coming from. So once again, I went to the source code, at least the directory, and I did a grep for did you mean, and found that this was coming from the UVM spell checker, which until that point I had no idea existed. So not to belabor the point, but if you don't remember anything else I say today, if you're having trouble finding something, go to the source code and look and see what's there. So now that I knew this was coming from the spell checker, it still really didn't help me at all. But I started looking in the documentation for include coverage to see what I was missing. And as Adiel mentioned earlier, you need to have the include coverage function call in your test. Now this is costly. As an example here, I have it in my base test, but you really only want to include it in a test where you're actually doing register accesses. There's no point to have it in every single test that you're running. So now that I've included that, the pesky warning messages have disappeared. So now I want to walk through how I've actually implemented coverage. I looked online and found a great example that I implemented and works perfectly. So that's what I want to finally share with you. So in my UVM reg block, I'm creating a coverage object, regcov. So in my build function, I first check to see if it has coverage. Well, it does because I built it with coverage. I had build coverage UVM cover all. If that returns true, then I use the factory to create my register coverage object. After that, I call set coverage UVM cover all. So set coverage is basically turning on all the functional coverage checks for that register or register block. Now next, I have a sample function in my UVM reg block. Now this function gets called automatically whenever you do a read or write access. So sample with an offset is read and the map that I'm trying to collect coverage on. So I'm checking, I have this call to get coverage, which is basically checking to see if you set coverage. So if you remember on the previous slide, I've set coverage. Now it's checking to see if I've set the coverage. If I have, then it's double checking the map name. Here I put default map. You would obviously use whatever map name is in your environment. And then once that returns as true, I'm calling the sample function and my coverage model with the offset and the read. So now in my coverage model, there's the sample function with offset and read, which then in turn calls the sample function of the actual cover group with offset and read. I have a cover point for the address, and I have a bin for each register offset. I then have a cover point for whether it was a read or write, and then my cross to cross the address in read and write to get coverage for every register.
My name is Peter D'Antonio from the MITRE Corporation, and this is Stephen D'Onofrio from Paradigm Works. We're going to talk to you this afternoon about our experience stacking verification components in UVM. I'll take us through the first half of the presentation. I'll go through some background, motivation for selecting UVM, and some requirements, and then some concepts. And then Steve will take over and go into some detail. So first, a little background about MITRE. The MITRE Corporation is a not-for-profit corporation chartered to work solely in the public interest. MITRE operates several federally funded research and development centers, or FFRDCs. And basically what MITRE is, we're a government advocate, and we find creative and cost-effective solutions to government problems. The organization I'm in, we work with communications, GPS, and radar systems. So prior to adopting UVM at MITRE, we had an effective verification flow for DSP that combined analysis, system modeling, and RTL verification. And we found it worked well in previous technologies, both FPGA and ASICs. It was, however, file-based directed tests, and we found that the capacity didn't scale with the technology that we needed. The project that motivated selecting a new methodology was a 45 nanometer ASIC, and that was a DSP data path design. And the project was schedule and resource constrained. The team was about 8 people, including Steve and myself, and we had 6 months to bring the team up on any new methodology and also to execute the project. So it became clear that also first pass success was expected, of course. So it became clear that we needed a step function improvement in our verification flow to meet these increased design complexity. So quick marketing slide. The motivation to select UVM as our methodology really hinged on three aspects: quality, efficiency, and leverage. First and foremost, we wanted to improve our functional verification coverage and ultimately the quality of our product. We felt that the foundation that System Verilab gave us of constrained random verification and coverage metrics helped meet this criteria. Second was efficiency. In order to recoup any of the investment that we put in to select a new methodology, as well as to keep up with increased design reuse through IP on the design side, we had to get more efficient through reuse on the verification side as well. And we felt that the recommended structure that UVM and the UVM user guide gives you really gives us a foundation to build our strategy upon and not have to worry about reinventing the strategy or the structure. And last and not least is we wanted to make sure that any methodology we chose had broad industry support and continued user momentum. And also EDA vendor independence was important to allow us to meet the flexibility of our changing customer needs. So to meet those efficiency promises I made on the previous slide, we first made some requirements at the beginning of the project. The first requirement was to reuse as much as possible wherever possible. Specifically, the UVCs were going to, all of our components at the lower level shared a single physical interface on the data path, but each one had a slightly different logical use of the same interface. So we wanted to make sure that the UVCs were reused across all of those. So UVCs had to have configurable behavior. The DUT expect models represented our single largest investment on the project, and they were going to be reused between the unit and the system level and potentially in future products. So we wanted to make sure those are as flexible as we could as possible. So we implemented those as UVM components with TLM ports. Also, we wanted to make sure we reused our test stimulus sequences. So we wrote those with abstract UVCs on virtual sequences. So just to define what an abstract UVC is here, that's a UVC that doesn't talk to an interface. So I'll show an example in the next slide. Where's my laser pointer? All right. So here's one problem, one protocol similar to one we faced on this project. We have a 3-layer protocol. This example is PCI Express. Ours was simpler than PCI Express, but it had the same stacking. So we have 3 layers: transaction, data link layer, and physical layer, where each layer takes a transaction from an adjoining layer, modifies it, and passes it on to the next layer. So for this example, let's just look at the stimulus side, because if we had the response side, we'd get out of control here. So we'd have 3 DUTs. Each DUT implements one interface of the protocol. And so one way to verify these 3 DUTs would be to have 3 separate environments, each with its own UVC that implements the appropriate interface. So you could do this. You'd have 3 separate UVCs, 3 separate environments. So this is a valid solution, just there's not a lot of reuse here. So one solution would be you have those same 3 DUTs. Your first environment for the transaction layer would look the same as it did in the previous solution, where you have the transaction layer UVC talking to your first DUT. It gets interesting in the second environment, where you bring over the transaction layer down to this environment and you use that as an abstraction layer, and that's stacked on top of the data link layer. So now you were able to reuse some of your sequences here to communicate with, but your data link layer is still talking to the DUT through its data link layer interface. Similarly, in the third environment, you get to bring over both the transaction layer and data link layer as abstraction layers, but the physical interface is communicating with the DUT. So here you've reused the UVCs several places, and more importantly, you reuse the sequences that came along with them potentially. So for example, you could have written a sequence here that generates address data transactions and then reused it in all 3 environments. It's important to point out here that you always have the ability to write sequences on any of the UVCs in any stack, regardless of the position. So here's a horizontal reuse solution. This looks more like what you'd expect for a UVM environment. In this example, we have our virtual sequences written for top layer UVC, and those are stacked on top of a DUT-specific bottom UVC. So in this example, we have DUT number 1, and you have you have a predictor that's specific to your DUT. So what separating the sequences from the interface for the DUT allows you to operate at a higher level of abstraction here, potentially. And also, you can swap out the lower level UVCs or the DUT to get reuse. So for the next, if we take away all the DUT specific stuff, these are all the things that you get to reuse between different DUTs that might have different interface UVCs. So you could plug in your next DUT with a different interface and a different predictor, but you got to reuse all of this infrastructure across your different interfaces. And do that again. Now, Steve's going to come and talk about some implementation details.
So this is an overview of the second half of today's presentation. At MITRE, my responsibility was to deploy UVM for the group. So in the second half of today's presentation, I'm going to take the UVM concepts that Peter just described and show you how we applied that into UVM. I'm going to go through a list of the implementation and concepts for the design, for the verification environment that we came up with. I'm going to go through a list of different implementation architectures that we needed to choose from, and I'm going to show code snippets throughout. So let me start out by talking about UVM. UVM offers many reuse techniques that are very valuable in meeting Peter's goals. We talked about the active-passive fields with the agents. That was extremely powerful so that we could create a single verification component, a test bench, and just reinstantiate it in multiple test benches over and over again. The UVM also includes a methodology in the user guide for stacking sequencer components on top of each other. This also helped us move in the direction of accomplishing what Peter was looking for, but there were steps above and beyond the UVM user guide, what's offered in the user guide in the class library that we needed to do in order to fully meet the requirements that Peter was just discussing. For instance, the user guide methodology or prescription for stacking is at the sequencer component level of abstraction. In our UVC components, we also need to take into account the monitoring path. So there's no prescription in the user guide for that. In addition to that, what we're looking for his reuse techniques are at the agent level of abstraction. We need some kind of agent interconnection strategy. So we came up with this methodology on top of UVM called stacking UVCs. And what I mean by stacking UVCs is that we want to create verification components that have the flexibility and the robustness to not only communicate through system Verilog interfaces to RTL, but also communicate to other UVCs, as Peter showed in his slides. And with that type of technique, we then meet the requirements that Peter was looking for in his project. So the first thing we did is we came up with a list of concepts and requirements, and it's shown in the slide. It's broken up into two major sections. First, the UVC requirements, and then there's this concept of an adapter package that we came up with. So on the UVC side, the first requirement we had is that we needed some kind of capabilities of either including or excluding a system Verilog interface in the verification component, some kind of configuration capabilities. The second requirement we had was that we weren't simply going to take a verification component and plop or reference another verification component in it. Creates excess baggage for reuse. And if you have a working verification component, you don't want to go in and modify the code. We've been talking about it all morning. If you have good golden code, if you start modifying it, you're going to break it. So that was certainly out of the question. So we came up with this concept of an adapter package. An adapter package is a system Verilog package that sits outside of the scope of the UVC itself and allows us to use inheritance in order to connect a particular verification component up to one or more other verification components. It includes transfer functions that allow us to convert from one transaction type to another transaction type. The adapter packages are going to be reused in multiple test benches. So they need to be able to handle the active-passive capabilities of the UVCs, and they also need to have some kind of configuration capabilities. We found as we were reusing these packages, these adapter packages from test bench to test bench, we would often have to go in and tweak the transfer functions depending on the test bench topology that we're integrating into and the connection scheme. So in this slide, I'm showing a simple UVC agent. Just want to take a quick sidetrack. The UVM user guide describes more sophisticated type of UVCs that have EMVs with multiple agents in them. And those were the type of components that we actually developed on Peter's projects for various reasons. The only reason I mention this, I just want to clarify, highlight that the stacking approach that we're talking about here not only applies to the simple UVC agent, but it also scales up to the more sophisticated type of UVCs that are described in the user guide. So this is a UVC agent that was very similar to the one that Tom discussed in his slides earlier today. For stacking, what we did is we added a has interface switch into the agent. And with the has interface switch set to 1, the UVC operates in the same exact manner described in the UVM user guide and how Tom discussed agents operate today, earlier. When we set the has interface equal to 0, we exclude the driver from being built. That allows us to take the sequencer and connect it to another sequencer in a different UVC. In addition, we don't connect the system Verilog interface as Vanessa showed earlier. Instead, we add a TLM port that allows us to communicate to this monitor. And this is the code that we added on top of a standard agent in order to accomplish this. We have an agent called top agent that extends from the UVM agent. It has a property. We added this property called has interface. And then during the build phase, we use the configuration database to set the has interface property based on the configuration database. And then if it's an active component and has an interface, then we build the driver component. If not, the driver component is not built up. Similarly, in the connect phase, if we're active and we have a has interface, then and only then do we connect the driver and the sequencer. Now I'm going to show you what our adapter package looked like. What we did is we have a monitor, a sequencer, and a configuration object here from our UVC. And then in our adapter package, we create extensions of the monitor, sequencer, and configuration object, adapter extensions. And we add an adapter sequence. And then inside our monitor, we add TLM ports that allow us to have interconnection capabilities. Then we add a transfer function in our monitor to convert from some other transaction type to our UVC's transaction type. And then in the sequence, we convert from our UVC transaction type to some other UVC's transaction type. And finally, we use the UVM factory to override the UVC's original monitor, sequencer, and configuration object with the adapter equivalent. And this allows us to have an adapter package inside our test bench that doesn't add any test bench topology. It keeps things simpler. So this was a requirement that we wanted to keep things as simple as possible and bring in an adapter package and have it not as much non-intrusive to the test bench topology as possible. So now the question is, where do we put the adapters when we're stacking up UVCs? So we came up with 3 different options, option A, B, and C. I'm going to start off with option A. And with option A, let me just go over the topology of this setup. We have an abstract UVC that Peter just described, and we set the has interface switch to equal to 0 in order to have an abstract UVC, the top UVC. In the bottom UVC, we set the has interface switch to 1, so we're communicating to RTL via system Verilab interfaces. And with this option, we put the adapter monitor and the adapter sequencer, the adapter monitor in the top UVC and the adapter sequencer in the bottom UVC. We connect the bottom monitor that sends up a bottom transaction into the adapter monitor. The adapter monitor will take that bottom transaction and convert it to a top transaction. On the stimulus side, the top sequencer will send a top transaction sequence item to the adapter sequencer, and the adapter sequence will convert that to a bottom transaction type. Now the problem with this approach is that the adapter's in 2 different components, and this adds complication. First of all, for our adapter, do we extend the UVC tops configuration object, the bottom UVC's configuration object, or both? None of these answers are ideal. In addition to this, when we started going down this path, we'd create, if we had 2 different top UVCs connected to the same bottom UVC and we'd utilize those adapters in a single test bench, there would be a collision when we use the factory overrides with the configuration object. So we opted to move away from this because of those complications. So the next option that we came up with was to add the adapters in our top UVC. And with this approach, the monitoring path is the same as I just showed on the last slide. On the stimulus side, now we have an adapter driver. So we added an extra component into our test bench topology. And the bottom adapter driver will take a top transaction and convert it to a bottom transaction and send it out its out its TLM ports. Now with this approach, what we found is the adapter driver is very similar to adding another sequencer component in the path. It adds extra performance overhead. So that was a really bad thing. In addition to that, in all the sequencers in our test bench, we had to add some kind of TLM pull ports into it, or maybe if you have a many to one connection to the bottom, you'd have to have an array of these guys. And this adds extra complication also. And then you need to take the transaction coming from the adapter driver into the sequencer. In that sequencer, you need to somehow grab that transaction and force it into the sequencer. So there was extra complication with that as well. So we opted against option B, which brings us to option C. And with option C, we added an adapter, our adapters in the bottom UVC. And with this approach, we send out, the adapter monitor will convert a bottom transaction to a top transaction and send it up to the top UVC. And the stimulus path is the same as option A. The only problem with this approach is that we have to add an extra analysis port in our monitors for all the monitors that we create. But all the other pros outweigh that one con as far as we're concerned. So we consider this the best option for us to move forward with. So I'm going to show you the extra code that we added in our monitors to allow for option C to operate. So And the example that I'm showing, we have the top monitor class. We had an analysis import that's parameterized with the top transaction. Associated with the implementation is the write method. Inside the write method, when it's called out, we do what you typically do on a monitor. You perform checks, integrity checks on the transaction coming through. You update coverage. And then you publish that transaction. And what I mean by publish the transaction is that we will clone the transaction, as Vanessa mentioned earlier, before we send it out the item collected port. So this is very similar to the code that Vanessa had in her slides, so that you can broadcast that transaction to other components that might be connected to it, such as predictors, scoreboard, so on and so forth. So now I'm going to show you the adapter monitor code that we put together. The adapter monitor, in our example, extends the bottom monitor. The adapter is called bottom adapter monitor. We add an analysis port that's parameterized with a top transaction. We call it top item collected port. And then we take the virtual publish transaction method that I showed on the previous slide, and we call out super publish transaction, and then we allow for the transfer function to be inside this publish transaction method. Inside here, you'd declare a top transaction like I just did, and you'd add application-specific code for your conversion from the bottom transaction to a top transaction. And then you send it out the top item collected port. And this write calls out the write that I showed on the previous slide. So that's all we needed to do on our monitoring path in order to have stacking of UVCs incorporated using the option C. Now I'm going to show you what we needed to do on the stimulus path. First of all, I just want to mention that we did not need to modify our original UVC sequencer code at all, like we did for the monitor. We simply create an adapter sequence as shown here, and then we add a TLM pull port and parameterize it with whatever transaction type you're trying to communicate with in your adapter. In this case, it's the top transaction. So we created a pull port called top seek item port in our sequencer. And then in our adapter sequence, we declare a bottom transaction, top transaction, and then we use this UVM declare P sequencer that will allow us to have a P sequencer, a pointer to our bottom adapter sequencer. And then in the body of the sequence, we operate in a forever loop. We're always trying to perform transfer functions when possible. So in order to do that, we call out the top sequence item port that I showed you on the previous slide, which is part of the sequencer. Use the P sequences to access that, and we call get next item, which was described earlier in presentations, and we request a top transaction. When there's a top transaction available, the get next item gets unblocked, and we send out that transaction to whoever's connected, to the driver, whoever is connected below the sequencer. Once that transaction's finished in the driver, we call out the item done on the top sequence item port. In addition, at MITRE, we had to deal with not only requests coming through the stimulus side, but also responses. So in order to handle responses, we declare both top and bottom request and top and bottom responses. And we have the same forever loop that we showed in the previous slide, except now we wait for a response to come back from the driver, whoever is connected below us. And then we get to convert from the bottom response to a top response, and then we send that out as an argument in the item done that's sent back to the top sequence item. And then as far as our test bench environment, in order to get our adapter hooked up, in the build phase we use the factory overrides to override the monitor, sequencer, and configuration object with the adapter equivalents. And then in the connect phase, we connect our adapter monitor to the top monitor. And then based on the active passive fields, we can then connect our adapter sequencer to the top sequencer. And finally, we used UVM 1.1 phasing. So what we did is we called out our bottom adapter sequence using the UVM database as a default sequence to operate in the run phase so that it's running all the time. It's trying to do this conversion. The adapter conversion is in the forever loop throughout for the entire run phase.
So to just summarize some of the results that we had using this methodology at MITRE, on this project we had 14 unit test benches and 1 system test bench, and with a team of 8 engineers over about 6 months. We were able to realize heavy stimulus reuse with our abstract and stacked UVCs, and the stimulus that we did create was easier to understand, to share, and to create, understand, and share, because it wasn't specific to the interface or the DUT. It's also important to note out here that while most of the stacking layers were 2 or 3 deep, we did have 1 or 2 4-layer stacks, so it scales up as many times as you want. We're able to get that full bottom level reuse between all of our unit levels on the data path, because again, every component had the same physical interface but a slightly different logical use. And we're also able to reuse our unit environment entirely in the system test bench, with only some modified connections on the DUT expect models to model the system topology. And also, we did hit our tape out on schedule and on budget, and we expect silicon in the lab in April. Well, that's the asterisk, right? I'll let you know next year. So in conclusion, Steve mentioned that the UVM user guide doesn't really provide an agent level layering methodology, but we shared our stacking methodology, and hopefully shows how you can create reusable UVCs and, more importantly, stimulus with the API and implementation that Steve shared. And so we've seen proven results on this project plus on successive projects at MITRE, and I know Steve has used this beyond MITRE. And just yesterday, Steve contributed a full working example on uvmworld.org. I think it's called Stacking Verification Components.
Yeah, and it operates on all 3 big EDA simulators.
So it works with all the EDA vendors and demonstrates all of the code that we have here.
So we have a huge problem with this at AMD. We started writing OVM over 2.5 years ago, somewhere in that ballpark. We have SoCs, and these are SoCs in the sense of full x86 cores, our high power core, our low power core, full GPUs, full Northbridge, full Southbridge, all using OVM code. Now, who has the luxury of stopping everything they're putting out, converting their code, checking it in, and then starting back up? Does anybody have that luxury? So we don't either. Putting out 4 to 10 SoCs a year with varianting and whatnot, everybody is like, okay, I think switching to UVM is a very good thing. Let's let that project 3 months, quarters, years down the road do that. You're not going to put any risk on my project converting my code line, causing me to branch my source code, causing risk in my schedule. I've got to be out in 2 months. Go away. And we're saying, look, there's people that have already transitioned, there's value in UVM, there's bug fixes, there's more ecosystem, there's more collaboration, there's more contributions. There's more debug tools, there's more verification IP, the list goes on and on. We must get there. But with a cadence of every several months putting out an SOC and all the IPs that get rolled up into these SOCs, no one ever really wants to stop and let us just check the code out, convert it, qualify it, check it back in. Even a day or a weekend or a week would be too much. So we had to come up with a way to transition the remaining OVM code into UVM. So we're going to talk about what we did, how we got there, and some of this stuff is like, okay, I could kind of see that, and some of the stuff is just mainly code line management of, do you branch your code? Well, if you have a sophisticated version control system and you branch your code and convert all your OVM to UVM, and then you find some nice little bug fix that goes in this, and you want to integrate that bug fix into this code line, how well does that go? The system says, hey, wait, I've got all these other changes, and it puts your O's back over your U's. So who's in favor of renaming the library OVM? Anybody oppose this? Janek's not laughing. So with that introduction, I'm going to turn it over to Justin. He came up with a couple of steps to get through to get you as close as possible and then to make that final leap. So.
Okay, so about a year and a half ago, John brought me in to start working with the UVM committee, the Accelerator committee, to do some of the work with him that AMD needed from UVM. And in that context, about a year ago, John and I had a conversation wherein he said, Justin, we do have a lot of OVM code. We have a lot of it out there, and a lot of SOCs in flight. And we're going to need to convert all of this code. And I kind of laughed, and I said, yeah, what sucker are you going to find to do that? Hi there. All right, so moving in, our main problem is obviously, how does one transition a company which heavily uses OVM into using UVM with the minimal amount of user pain? Now, John kind of touched on this, but it's been my experience that if you go to a group with a library and say, okay, we have a bug fix, right, the group will gobble up your update to that library. They will be perfectly happy about it. If you go to that group and say, we have a bug fix and a little bit of new functionality, but you don't have to change any of your code, everything just kind of stays the same, they will gobble it up. You go to that group and say, we have enormous bug fixes, enormous functionality improvements. You have to change about 3% of your code. They will sign off on that 2 years from that date. All right, that's when they're willing to do it. And now our SOCs have quite a few IPs in them. So they're all going to choose 2 years from whenever you talk to them. Nothing is ever going to line up quite right. So we really had a problem on our hands when it came from converting all of our O's to U's and minimally impacting our IPs. So to look at where we were about a year ago, we have many interface, module, and system level OECs from multiple SOCs that are in flight. All right? You're looking at thousands of lines of code in multiple real-world projects. With all of that code, we very early on realized that we needed to do some sort of sanity management for OVM. We didn't want all of our IPs going off to OVM World, downloading the OVM library, doing whatever they wanted to with it, and then trying to integrate that all together at a higher level. So we put it all in one central location. And the version that's in that central location right now is 2.1.2 plus a couple of bug fixes that we've found. In addition to having the library itself in that central location, we built what we call the OVM kit. All right, now the OVM kit has items that we found to be extraordinarily useful and extraordinarily reusable. So back when you were looking at OVM 2.0, you had the objection package in the kit. All right, that eventually got folded into the OVM library, so we removed it from the kit. You have the command line processor contribution is in the kit. And then in addition to that, we also have something very similar to what Vanessa was talking about with an interface registry in the kit. So just a common way for all of our IPs to use OVM. Now, we weren't trying to push so that every IP wrote their code exactly the same way. With the sheer amount of code that we were dealing with, that's unrealistic. What we wanted to do was make sure that they were compatible with one another. All right, everyone's using the same version of the OVM library. Everyone's using the same version of whatever contributions we happen to put in there. Now, where we'd like to be is UVM. Obviously, we're all in a room labeled UVM. We wanted the register library. All right, back in OVM, you had 2 vendor contributions for register libraries, but neither one was officially a standard. UVM, we actually have a standard now. We wanted the resource database and everything that came along with that. We also wanted the industry support, because who doesn't like going to Eastern Europe and getting more VIP? So let's do that. We want as much of this as possible. So we really wanted to go to UVM. Now, when UVM was originally kind of spoken of, everybody thought this was going to be really easy. All right, you would just kind of grep for O and replace it with U. And, well, you hit some issues when you do that. So the first issue that we hit was UVM removed things that had been deprecated in OVM. All right, the best example of this that we have is the sequence constructor in OVM. Sequence constructor in OVM has 3 parameters to it. The latter 2, the sequence pointer and the parent sequence, or sequencer pointer and the parent sequence, are both deprecated. All right, you're not actually intended to use them anymore. When you call start on the sequence, you pass it that information. In UVM, they removed those deprecated parameters, and therefore, if you just did your simple O to U grep, you were going to get all sorts of miscompiles on every single sequence you had that utilized those parameters. All right? That's kind of an obvious one. There's a much trickier type of issue that we ran into, though. And that's one where they changed the parameters in methods that weren't deprecated. All right? Here you have raise objection. So we have heavy usage of the objection mechanism. And in UVM, there's even heavier usage of it. In raise objection in OVM, you just had 2 parameters. All right? You had to pass in the object on behalf of which you were raising the objection and the count that you were raising it. All right? Nothing too complicated there. In UVM, they added a description, which is great. Now you can say why you're raising the objection. For debug purposes, this is wonderful. However, and I'm going to say I was not in the committee when this decision was made, they dropped the new parameter in between the other 2. So, depending on...
John was there.
Yeah. No, finish though.
I'm curious, what did John have to say?
It didn't go nicely, did it?
It was John's idea, too.
Wow, that bus has a lot of wheels, Tom. You're just... Yeah. So this is very inconvenient, and depending on which simulator you're running on, this can bite you a couple of different ways. But the moral of the story with these 2 items is that the grep O to U really wasn't going to work for us. The other big problem we have, and John touched on this, is we have quite a few SoCs in flight. All right? And please don't take my simple diagram to think we only make 4 chips a year. All right? And each one of them is overlapping in various stages. You have ones that are at the, hey, we picked a cool code name stage, and then you have ones that are actually approaching tape out. The closer you get to tape out, the much more resistance we hit with regards to pushing even bug fixes. It gets difficult unless, the bug fix is going to help them tape out. They really don't want to change. So we didn't have the ability to just take all of our code, lock it for any period of time, run any form of conversion on it, and then unlock it. All right? If we caused 1 day of slip, that was simply unreasonable. Couldn't do it. Right. So that led us to the concept of what about coexistence? All right? So you've got OVM, you got UVM, and since they did change the letter, we know they're not the same. Therefore, in theory, we should be able to build them together. You cannot do that with UVM 1.0 or UVM 1.1 because they shared file names. All right? In OVM, you had base.svh. In UVM, you had base.svh. In addition to that, since you were dealing with two different packages, you're dealing with two different types of base classes, all right? OVM object and UVM object are two different things, all right? They're coming from two different package scopes. If you were to try and connect a TLM port from UVM into OVM, at best, you'd get some really interesting results. At worst, you would get a horrible, horrible compile, all right? This changed a little bit with 1.1a, okay? In 1.1a, we changed base.svh to UVM base.svh. We changed TLM and all of the other ones so that they were all prefixed with UVM under. So now you can compile UVM 1.1a in addition to having OVM present, all right? You still have that TLM problem, all right? You're going to have to build translation layers, something like an O to U FIFO, and a U to O FIFO, wherein OVM is coming in the one side. Internally, you translate all of your, ints, you're just copying over. Anything that's based on UVM object, though, you're going to have to get the appropriate OVM object and set it up so that you can copy it. Events work, and events can get copied over. Enumerations become difficult. Really, it's a hassle to do that translation. And that hassle is throwaway work, okay? Once you've officially moved to UVM, all that stuff is just going away. You can't do anything with it anymore. Then finally, even if you did get all of the TLM stuff working, you have the problem of synchronization, all right? OVM has the run phase, which is running with OVM test done as the primary control mechanism for it. UVM introduces the run phase. Now there's an underscore in between there. You can't see that when I say it, but the UVM run phase is controlled by its own objection. Those are two different objections based on two different base classes, so you can't do any real trickery there. And then UVM has all of the actual runtime phases, and that's just another headache. Now, that being said, you could do all of this. You could create a walled garden. All right? You could figure out the TLM translations between your O's and your U's and copy as much by reference as possible. And you could figure out the synchronization issue. All right? All of these things do have solutions. But every last line of code that you're writing to make all of that happen is throwaway work. All right? Hopefully in 2 years you have now migrated your code to UVM. You're not relying on the OVM library, which isn't particularly supported. And I'm talking 2 years from now. And hey, if vendors want to keep supporting it, more power to them. But Eastern European countries are going to be making UVM code. So you really want to get to UVM. So all of that work is really throwaway work. All right? So we can't do a simple O to U. And we can't really do a walled garden approach. That's not really going to work. So here's what we did. Our first step was to attack the deprecation in the user code. All right? And this was a big step. We created a new version of our OVM kit where we took the OVM library, 2.1.2, and we removed anything that was deprecated in OVM that was flat out removed in UVM. All right? So we actually took out the parameters from the sequence constructors. All right? We took out a whole bunch of stuff from the compatibility layer that was in there. That's all code coming from URM, AVM, all that. That all got wiped. Okay? This was not easy to do, and it's taken a few iterations. And the reason it's not easy to do is because OVM doesn't have an OVM no deprecated switch. UVM does. If you build UVM with that tick define set on the command line, you don't get any of the deprecated code in UVM. You are guaranteed to be running whatever the most up-to-date non-deprecated functionality is. We personally think this would be a great place for kind of a one last hurrah vendor contribution to OVM world. All right? If there could be a version of the OVM library or with a single tick define, you're guaranteed that just about everything you do will translate very nicely into UVM via a simple script. That would be incredibly useful. All right. So when we did this and we pushed it out, we kind of snuck it in a little bit. We told them it was a bug fix. All right. Turned out their code had bugs in it. They didn't know it.
Bug fixes.
Oh, yeah. So this cleaned up all of the user code. Now, the users are still using OVM code at this point, all right? But they're not using any of the deprecated stuff. And with rare exception, most of the teams were willing to make this step in the name of removing deprecation, all right? But there were some teams out there that were a little bit too smart. And they were able to figure out this wasn't just a bug fix. They were getting duped. The one thing that we did have going for us here, and that made a lot of this easier for the end users, is that the code which was running on our new modified version of OVM was guaranteed to run on the old version of OVM. All right? We weren't changing the functionality of the base class library. We were simply removing the deprecated items from it. So if a team were to write code based on OVM 2.1.2-transition, and then they had to deliver that to a team that was just running OVM 2.1.2, it would work. All right? Their code was perfectly functional, perfectly legal OVM code. For all intents and purposes, we invented that OVM no deprecated switch, and we turned it on. All right. So, after that point, you're translatable, kind of. All right. Your code can now be processed by a Perl script or Python, or pick your language, and your O's can be converted to U's, all right? Now, there's a script that comes with UVM. It's in the bin directory, and it is designed to do just that, okay? Convert your O's to U's for you. It's not perfect, all right? But it is a great template for any company out there who needs to do this. That's a great starting point. All right. One of the items that we know for a fact it doesn't catch, the raise and drop objection conversation from a few slides back there. If it does see a raise objection with 2 arguments, it will modify that so that the second argument becomes the third argument. Same thing for drop objection. But it doesn't catch the callbacks that were associated with raise objection and drop objection. You had raised, dropped, and all dropped. It doesn't catch those. So if you were using any of those, your code's going to throw an error. All right, if you used the version that's currently in UVM. So at that point, like I said, you're translatable. You got to do some work with the script there, but you're pretty much there. But that didn't really solve our other big problem. The fact that we have so many SOCs in flight, that kills us, because we still, even if that script worked 100%, got all of it converted, there's no way an SOC is going to let us lock them for, let's say, a Friday. All right, we're going to get them on a Friday and tell them, this weekend you don't get to run your regression, okay, because we're going to do something special to you. And then we run our script, and we check them in so that on Monday it works. The ideal scenario. No one's ever going to believe that that's going to work. They're not going to let you try that. All right? You have to prove that to them over and over and over and over again. Do it 5 weekends in a row while they're still running regressions, and then maybe they'll let you do it in 2 years. So we still had to work out exactly what to do with that. Then we kind of had this inspirational thought, courtesy of some things that we had seen contributed to OVM World. And that was, we built a backports package from UVM. All right? We knew that the resource database was brand new, and it was disconnected from components. That was the intent behind it. So if it's brand new, disconnected from components, we can take it and convert all of those U's to O's. And now you have an OVM resource database. You had RAL. Something very similar can be done with RAL. That was contributed to OVM World. There is a UVM, I think it's called UVM Reg, but the RAL package is available for OVM on OVM World. Then there was UVM callbacks and all of the macros that they provide. And, you know, the list just kind of goes on, things that can be backported into OVM. This allowed IPs and any SOCs which weren't really ready to jump all in to UVM. They could see some of the newer features. I mean, the fact that we now were able to give them an OVM, a register library that was basically a standard, all right? If you bought your Eastern European VIP and they use UVM register, no, it's not going to work with our OVM reg, but you're close. You're really close at that point. And then, John's whispering something to me. Hooks, fully compatible.
Forward compatible.
Oh, forward compatible. Yes, it's forward compatible with UVM. That's what he's saying. All right. But we didn't want to just give people this for free. All right. You give it to them for free, and they're never going to go to UVM. So we did a little bit of a bait and switch. We told them that in order to get all of these backports, you have to move forward to the transitional version of the OVM kit. All right. You don't get the UVM features without removing the deprecation. All right. Now, my plane yesterday had a little TV on it, and the channel was broken, so I watched Mary Poppins on Broadway for about 7 hours, that commercial. Spoonful of sugar helps the medicine go down. All right. That is exactly what we were doing with the UVM backports. Anybody who wouldn't do it just in the name of removing deprecation, well, if we introduce a forwards compatible register library to them, that got them. All right. So that brings us to the third step. We're still trying to fight that SOC problem, okay? You can't just change their code on them. So we have IP code, which we know is translatable, and we have SOC code, which we know is translatable. What we do in our third step is provide an on-the-fly translation script, all right? Now, this is meant to be run when the IP publishes into the SOC. I could see that point right there. This thing has a little blinker on it. There we go. Meant to be published there. That could potentially lead to confusion here. So different companies call this step different things. The important thing is that your IP is going to get to a point where they're delivering their source to the SOC, all right? Somewhere between that point and the SOC actually compiling the code, somewhere in there, label it publish, okay? And that's what we're talking about. The IP has verified their code, and they verified it with OVM. They have the ability to throw a switch and run this on-the-fly script, so now they're running their OVM code converted to UVM. And they can put that into a sanity test if they need to. And now they know that their code is both OVM compliant and UVM translation compliant. This gives an SOC the ability to make some choices. One, the SOC could stay at OVM until tape out. All right, like I said, there are some SOCs where, short of pointing a gun at someone's head, they are not going to change to UVM. They're just not going to do it. There are also SOCs that are early enough in their schedule that they're willing to transition to UVM before they tape out. They started as OVM, but they're going to transition to UVM. If they decide to do that, then any IPs that are delivering into that SOC will now get run through what we call the mutator script, all right? They're going to get run through that mutator. And the IP is verifying their code as OVM. They have to run a sanity test to make sure that it mutates properly as UVM. But then the SOC now is running UVM code. The final choice that an SOC can make, and this obviously only applies to SOCs which are coming in the future, they can decide to start at UVM. Now, any IPs that are delivering into those SOCs, if they already had OVM code, basically C is no different than B. All right? They have to be able to write their OVM code and have it be mutated into UVM code before the SOC actually executes that code. But any new IPs now have an opportunity to start at UVM code. And that's an important difference, because the IPs which are mutating from O to U, they're not really 100% UVM there. They're OVM that's been converted. So you're not going to see run under phase. You're going to see run, which technically still works in UVM. It's just been deprecated. All right? You're going to see a lot of stuff like that in this code. But the code that's starting from scratch as UVM gets to use all the non-deprecated features of UVM, the things that you couldn't do in OVM, even with the backports package. Now, that was a great idea, and we had to go through a couple of revisions of it because we hit some speed bumps. All right? Turns out that there is actually an additional category, not just deprecated code and code that wasn't deprecated but was changed. You have things that were just completely not deprecated. All right? This is the way they worked in OVM, and this is how they were spec'd. This is the way everything was intended to go. Specifically, the one I'm talking about is OVM phase. All right? If anyone ever actually used OVM phase, there's no great way to translate that. All right? I mean, that would be one heck of a Perl script to try and figure out what you were doing with OVM phase, transmorgify it into something in UVM. Probably not UVM phases because they work quite a bit differently. In order to get around this problem, we had to work with our end users, and we basically had to replace what they were doing. Now, we knew that phasing in UVM was heavily dependent on objections, and we had been using objections in other places, so we wound up creating an objection-based phasing mechanism for OVM, which, while it wasn't the UVM phasing solution, we knew that when we translated O's to U's, it would work. Once the translation is kind of complete and these teams are fully UVM, we have more work to do in the future. All right? We're going to have to take that code and kind of tweak it again to make it fully compliant with whatever the UVM phasing mechanism is. All right? Whatever parts of it need to be connected there, we can do that. And that brings me to kind of an interesting point. Everyone today has been showing best practices for UVM. That's not actually what we're talking about here, okay? Our number one concern is to get the OVM code into UVM, all right? Once we're in UVM, then we can start hammering, the best practices drum. But until then, our number one priority is just getting the O's to U's. So for a lot of the code that we're talking about translating, in the future, there will be more work where we will have to work with each one of the IPs and get them, moved up to non-deprecated UVM code. All right, I think it would be a fun experiment once we actually go to UVM to turn on that UVM no deprecated switch and watch everybody's test bench fail and scare the bejesus out of them. I have kind of a sick sense of humor with verification. But that is something that we know that's coming. All right, we know that eventually we're going to have to jump that hurdle. We're just not aiming for that at the moment. In addition, there was one other gotcha. This one really nailed us. And even though I think we found it on day 1, and then we rediscovered it on days 3, 7, and 25, this thing just kept biting us, the same bug. You'd think we would have learned. UVM's run phase works differently than OVM's run phase. In OVM, if you're using the objection system, the run phase would simply go. All right? It was going to run until someone stopped it. The way you would stop it with the objection system was at some point in time you'd raise an objection, and at some point in time later you would drop an objection. And when it detected that all of the objections had dropped, they had gone down to 0, and that's important, it had to be raised first. It went down to 0, only then would it end the run phase. UVM doesn't do this, okay? And there's very good reasons, and depending on how much time I have left here, we're pretty close to the end. We can go into exactly what the reasons are, but UVM changed this. So the way UVM works is once the run phase starts, you have one non-blocking assignment region worth of time to raise an objection. If you do not raise an objection in that amount of time, UVM is going to do everything within its power to end the run phase. So if there are runtime phases that are progressing, they have the ability to continue prolonging you. But if you didn't raise an objection in that first non-blocking assignment region, And since your translated code, you're not using the UVM runtime phases, your test just ended at time 0. All right? No errors, no nothing. Test just ended. Like I said, bit us about 15 times. Now, UVM provides a plus arg to help with this, all right? It's not particularly well documented. You can find it in the README, but I couldn't find it in the reference guide. It's UVM use OVM run semantic. What that does is it makes the run phase in UVM work the way it used to in OVM. Yet it doesn't matter if you raise an objection at time 0. In order for it to end, an objection does need to be raised and then dropped. All right? We could have used that. The difficulty with that is it would mean telling all of our SOCs and any IPs which are going with UVM that if they're running in a heterogeneous environment, and not even necessarily one where there's translation taking place from O to U, somebody may have migrated all of their O's to U's. They might be delivering UVM code that came from OVM code. If anyone in the environment's like that, well, you have to add this plus arg to your simulation. That's something we didn't want to deal with. So instead, inside of the UVM kit, which we have now, we added a run phase prolonger. All right? It's just a single component, and at the very beginning of the run phase, it raises an objection. And it just waits. And it waits to see someone raise an objection. And when anybody else raises an objection, the prolonger drops his objection. So it basically gives us the OVM run phase semantic in UVM without doing anything with a plus arg that every single one of our simulations needs to run. This falls under that category of eventually we're going to have to change this. All right? We are basically intentionally mucking with the way that UVM is operating the run phase. Someday we'll have to tackle that, but not today. Today we just want the OVM code translated into UVM code so that we can pay some people in Eastern Europe to give us some good VIP. And that's what we want. So eventually, once we have everybody translated, we get to our final step. We have a UVM environment, all right? John and I both take very long vacations, probably not together, and there will, be 2 weeks where AMD will be blissfully happy because no one's screaming about O to U anymore. At that point, then we start working with all the details of getting people up to best practices, okay? Any new IPs can start from scratch at UVM and they can use the best practices. Any new SOCs can do the same thing. Any old IPs can be converted locally from OVM into UVM, and then they can just check in the UVM code, and they're done. All right, their conversion is complete. They are now, from that point forward, delivering UVM code. And at that point, we have accomplished our goal. All right, we didn't stop any SOCs. We didn't hound the IPs more than a normal amount. And no one, throws up their hands in a fit and says, absolutely not. We can't afford to do that. That'll slip the schedule too much. Because the SOCs had the ability, they had the choice, they drove the bus, basically. The SOCs, when they all decide to go to UVM, now the IPs can fully go to UVM, and that's it. At that point, we are UVM. So that is the end of the presentation. We back up a bit here. If anyone has any questions, we'd be more than happy to answer them.
Okay, so what we wanted to cover with these user sessions was some of the experience that the users have had with UVM. For us, this was a transition from other methodologies. And the other methodologies, we had built certain thin shim layers on top of in order to accomplish certain things. And we're really seeing how we can accomplish that with UVM. What has UVM solved for us already? What do we still need to build on top? So first I want to go into what is our design paradigm. And this is actually something that we are migrating to. We haven't been completely doing this, but the next wave is really going to be following this exactly. And the idea is that we are going to be building ASICs, which all look pretty similar architecture-wise, but they might range from low performance to high performance. And the way they're going to do that is to have a certain library of blocks there that we can put together in various ways. So we might put together a lot of these blocks and make a very high-featured ASIC. We might put just some of these blocks in as a more low-featured. We might put more of them in parallel and it's higher performance, or less of them and it's lower performance. Now as we do that, you'll notice on this diagram here, I've got some, I've probably got a lightsaber here, right? Yeah. I put these little ticks here. It's not always going to be the case that we can just take these blocks and dump them in an ASIC and say, whoops, we're done, right? That would be, we could put a few people out of work if we did that. So there's still going to be some modifications that are going on here. So from a DV perspective, we need to know how can we do the same kind of thing here. The designers are going to be taking these blocks, maybe making some small modifications, in some cases having to add a whole new block for this particular ASIC, and we need to be able to build up a DV environment quickly to do the same kind of thing. So this is our matching paradigm. We want to have a library of verification components over here that then build up a test bench in much the same way. So here's our DUT, and we're going to drop in these components. We're going to introduce some terms here that Cisco's made up that some people don't like, but there are terms. We have the concept of verification components that are based on interface. These are the traditional ones that you've seen in the presentation so far. They have a monitor, driver, sequencer, in an agent, and so on. We also want to have another component which is an MVC, module verification component. In the diagrams you've seen so far, you've seen a scoreboard, right? People build up their whole test bench by dropping in the agents together with a scoreboard. You'll see we've got a few other things we want to drop in together with a scoreboard so that we can have these sitting in our library and drop them right in. So once we want to test this particular block here, what we're going to need is the interfaces that go on either side, the module that corresponds to the behavior that we see in this DUT, and of course we're going to have something for reset and clock. So we've got a few shared ones. Register access is another example. All right, so how do we support this kind of library-based mechanism? One thing is we have to have this structure be very flexible, right? You can say, oh, we're going to drop all these things into a library, but DUTs can be quite different, right? There's some DUTs that are just sending traffic from one side out the other. There's other DUTs that are more processor-based, and we have to be flexible the same way. We want to avoid having multiple instance statements for each verification component. What that means is we'd like, from a test bench standpoint, just to say, I want to include this element from the library, I want to include this element from the library, I want to show you how to connect them together, and I'm done. I don't want to have to say, I'm putting in this component, and I've got a line here to say how it instances into the main DUT, and I've got another line that says how it connects to my register mechanism, and I've got another line that says how it connects to my config mechanism, and so on. We also need a very handy checking scheme that can be changed easily, right? So because there's the possibility that the designs are going to make these small modifications, we need to be able to respond as nimbly from the checking standpoint too. So we're going to have our verification component, but we need to be able to go in and say, let's make the equivalent modifications that the design just made. We need a way to ensure the coherency among configurations of library elements. That means that as we drop in these library elements, they've all got their own configure block because they have to, right? We just pulled them out of the library. They didn't know that they're going to be with anybody else. And they're going to have some default values, and they're going to come up in certain ways. But when we pull them all together, in order for the environment to work correctly, they've got to have some of the values that are actually make sense together. Maybe they have to have the same knowledge of how deep a FIFO is, or maybe when you pick something to be very small, the other one needs to be very small too. You couldn't have it be large or the whole thing's going to break. So we have, one of the things we're going to talk about then is a scheme for making these configurations actually be coherent together. And the final thing I'm listing here, there's a few other small things we do, but these are the main things. the final thing here is a way to synchronize the behavior of these library elements. So again, because they're coming from a library, they don't know what they're going in together with. They need to have some scheme that tells them, here's what you're supposed to do at certain times, and just by instancing these two things together, they will plug into each other and say, oh, I know when I need to wait for anybody else out there, and I know what to tell everybody so that they wait for me. Okay, so this is our typical dot block environment in Cisco land. Everyone's varies. Ours vary too, but to a large extent, we're doing networking type applications where a block is taking some packet, it's doing something to it, it passes it on to the next block, that does something to it, passes it on the next block, and so on. So there's sort of a stream there. So our typical dot block here is going to be sitting between two other RTLs. It's going to have some traffic that's passing downstream, and there's going to be some kind of flow control or response coming back. And typically they're going to share reset and clocks. We do have certainly reset domains, but if you're sitting in the middle of one of those domains, this is what it looks like. Now, of course, there's blocks on the periphery that will look a little bit different, right? This block here, maybe stuff's coming from off chip. This one is driving off chip. But there's a whole lot of blocks in the middle that are really just interfacing to other RTL blocks, and they're sharing reset and clock, kind of all in the same domain. For that typical environment, this is the kind of scheme we want to get then. We want to be able to replace the RTL that was on either side here with our interface verification component. So now this thing is responsible for producing the response and for taking whatever our DUT sends. And this guy up here is responsible for sending our DUT some interesting things to work on and making sure that our DUT actually responds correctly. And we have this module verification component that we want to plug down to do the checking aspect and a few other things. We'll get to him in a little bit. But essentially this is the analysis port that we've seen before. These guys are going to say what happened over here, and they're going to tell our checking scheme. And for our common resets and clocks, we've got some other interface verification components, right? They're going to be sitting over here. Now you notice here I've got a dotted line. So this IVC here in this particular scheme has no real need to look at a reset signal. And so in some cases this is a virtual connection here, right? It's not actually going to go down to a wire and get that. It'll get passed information directly from the reset IVC. So one last thing I want to note on this picture is so we grabbed this guy from the library, we grabbed this guy from the library. It could be that in another application we want to verify an RTL block that's over here. In that case, this IVC is still the same thing, but it needs to behave a little bit differently. It doesn't need to drive the response back this way. It's now going to have to be like this guy here and drive what comes down here. So we're going to see the insides of the IVC where that comes into play. So in the pictures we've seen so far, we've seen that an agent contains a sequencer driver monitor with its own config. One thing that we make use of sometimes is wrapping these in another environment. That can come into play if there's cases where we really want multiple agents. There's certain applications where we're driving multiple streams. We really just want one thing from the library plunked down and be able to drive all these multiple streams. So having another wrapper around there helps out there. We don't need it all the time. There's times when this environment out here contains one agent, but for commonality and of usage, we just always put the environment around there. It's just easier just to say, you're going to get an environment in there and you're going to get an agent below it. Okay, so this is the normal scheme here, and we see that in this case we're saying the driver is going to come out and drive the signals that are going this way, and the monitor is going to look at the signals coming back, and these ones here. But we want this guy out of the library to be able to work in both modes here, right? He's got to be able to test the upstream DUT as well as the downstream DUT. And so as a standard practice, we make available another sequencer driver pair here to drive the other direction. So before, remember, we just had this guy who was driving this way. Well, in the case that we're testing the DUT the other way, we're going to have the sequencer driver drive this wire. So getting to the MVC question. So what we've seen on the picture so far is the scoreboard, right? So the idea is that you get from the monitor's analysis port feeding both sides of the scoreboard, you can do all your checking, and that's really nice. But there are a few other things that we typically need to do for our DUTs. A big one is the initialization sequence, right? So there's a certain set of register writes and perhaps reads, polling stuff that we're going to need to do because of a particular DUT. And it's very convenient to pull this out of the library as one thing, we drop down, and now we're going to get our init sequences for free, right? So the init sequences was the major usage. But we often, and again, this is sort of DUT specific to us perhaps, but it's very common that we want to have some counters here. Our DUTs count all kinds of packet statistics, right? So as we're going through the scoreboard, we typically want to have some information from the scoreboard going into a model of counters that we will then compare against the actual DUT counters. And we will have a config element in here, and this often can be shared across the scoreboard, what checking we need to do here, as well as the init sequences. So again, it was nice to have these together and readily be able to share this kind of information. And there's a few other things that we occasionally put into the MVC, sometimes the interrupt error handler connections, things like that. So having built this wrapper around it and said we're going to have something that contains a scoreboard and other things, we have found more uses for it. But the prime motivation is really these two, that whenever we pull this guy out of our library, we know we're going to need those two things, and we want them together just to get them easily. Okay, so we've come up with this scheme. We've told people we want you to create these IVCs and MVCs in the style that we just showed right there. But if we just told people, hey, go ahead and start coding that way, we'd come up with a bunch of code that looks quite different, and it would really be quite difficult to pick up somebody else's code and know immediately how it's going to work. And that goes against the whole idea of what we're trying to do with the library. So our solution for that is that we've gone to these code template engines. And the reason is that inheritance really doesn't provide a full solution because there's different configurations required at times. Sometimes we need a single driver. Sometimes there's a list of drivers. Various things like that make it very difficult to make one component we could inherit off of and make sure that all of the names and everything was the same. We can encapsulate these kind of rules in a template, and we've done that with some toolkit that is available on the web. So there's this open source toolkit thing, and there's a number of these. You wouldn't have to pick this one, that were really built for making HTML pages. So a lot of the people that have gone off and made web pages have decided it's crazy for us to keep writing the same code over and over. They have done the template work for us. We just need to provide the input and the pattern that we want, and go off and do that. So let me show you an example of the kind of stuff that we've got in there, and hopefully that's not too small for people to see. And all I've really shown you here is the build phase, right? So a lot of what's in these templates is going to be build phase, connect phase type stuff. What we're really hoping for is some kind of naming scheme that we've got here. So we want to know that when you get into one of these agents, the sequencer is always named SEQR, the driver is named DRV, right? The interface has a particular, well, no, the interface doesn't have a particular name. That's one of the things that the template would allow us to change, right? So we can feed into the template what we would like our interfaces to be. How many interfaces do we have? How do they hook up to drivers? All that information can be captured in sort of a questionnaire style. And once we've got that information, we can then put it in a standard way into some code. So let me just run through some of the things we see here. So I'm building up something I'm calling my IVC agent. I'm going to tell it I want to use my interface for that. Then based on that, it's going to give me a standard name here of SIGs. If we had multiple multiple interfaces, we would have a standard name based on SIG, so that everyone knows if I want to get things from the interface, it's going to be SIGs with some standard prefix, suffix if we need that, dot, whatever, right? That's how we're going to get stuff. Like I said, one of the reasons we might need this is there might be a list of drivers sometimes, right? So in this case, we've said we're producing a single driver, but if the person writing this IVC said, I really need a list of drivers, then we're going to have DRV be an array, but it's still got the same basic names, the same basic rules. We want to make sure that sequences have a standard path to the clock, so we make sure that our sequencer has the interface as well. We want to make sure that we're using common config that we've put in. So you'll see here that we have changed the active notification from upstream active and downstream active to upstream, downstream, and disable. Upstream and downstream, that was the difference between which one of those sequence driver pairs are we going to use, or are we actually going to turn on. The disable is sometimes we found that we've got these things in here and we really want a way just to shut them up, right? There's a monitor in there that is in the middle of a stream, and for whatever reason it's not really needed for our test, and it's got some problem with the type of traffic we're sending through it. We just want to shut it up. All right, so we mentioned that one of the things we need is an easy way to change our checkers so that they can update as nimbly as the RTL changes. And the way we're going to do that is have a standard scoreboard scheme with a very standard structure that is very modular. And we can go in and change one of these modules. So everywhere I've got these ovals here, these are virtual functions that I'll be able to go in and override. Lucky for us, you know, we can use a scoreboard almost all the time, right? Your mileage may vary. You may need other types of checkers, but we can really rely on this scoreboard doing 95% of our checking. So from a very high level, the idea is that we've got some upstream analysis ports. Often there's one, but there could be multiple ones coming in here. And the same thing for downstream. There's usually one, but there can be multiple ones. They come into some kind of transform function that decides how these things might change as they go through the dot, and then we compare them. But we need to dive down a little bit further. So this gives you a sense of it. Again, there's a few more, but the basic idea is that we've said, what are the things that we need to do in the scoreboard, and let's make sure that we have every one of them compartmentalized so that we can change any one of these individually. So just running through this, when we get an item from upstream, the first thing we decide is what kind of transform do we need to do. Sometimes it's going to be toss the whole thing. If this produces null, we drop out and we don't do anything with it. Then there's this more fuzzy logic thing where it's okay to drop. So often we'll say, you know, this thing's come in. It might get dropped. It might not. If you see this thing come out, that's okay. If you never see this thing come out, that's okay too. Right, so here's a routine to determine if it's that kind of thing. If it is, it'll mark it, and so we can use that further on down here at the match time. Then we decide which kind of stream to go in. So our scoreboards aren't necessarily all posting on the same list, the same array. There might be multiple ones that we're containing there. All right, so that's the upstream side. Something came in here. We eventually decided to put it on here. We might have marked it in various ways. Then something comes in the downstream side. Again, we can transform it and say, oh, that one, you know, really, we know that one got dropped. We don't care about it. We'll just make him null and nothing else happens here. Then we go into a scheme that says, is it okay for this thing to arrive early? You know, there are some cases where the downstream arrives before the upstream, and you go, why would that be? That sounds crazy. But that usually happens when there's some kind of error happened in the packet. So if we send something in and we error it, often the downstream side can see the error first, and the upstream still blithely sending away, even though it had this error back here. And the downstream comes back and says, oh, I've seen this little runty packet here, and we want to be able to put that somewhere to say, okay, let's match that against the errored packet up here and see if the runt made sense. Not always going to be the case, but we really need to think about all these little cases in here so that we are able to change it. Then we need to decide which stream is this going to match against. So it does a similar function up here. It decides which of these. It gets one of these streams. It grabs a match. So it decides which value out of here do we grab. It could be the one that's up front, but it could also be that this is some kind of out of order dot, and it needs to go look through the whole stream and decide which one of those is the real match. And then finally, once it's matched something and decided that it passed or failed, it needs to update the stream after the match. So we need to decide, what do we do with this? If we had out of order things that we picked up, we might want to say, if you find something, everything that came before it needs to be tossed. Like, we don't need that anymore. So that could be a case where we do an update. All right, so I showed all those ovals. What this leads to is a way to modify the scoreboard. So if we come in here and say, for this particular dot, I'd like to change the way the downstream transform works, and what I'm going to do is modify it based on the port num. So I'm not showing the code that I did here because I totally made up this example, but if there was some method that I already had created for modifying by the port num, I can grab this piece of data, go ahead and do the normal copying the value, and then go ahead and modify it, and then return the result that I got there. Right, so now I'm going to compare against this modified version and not the original thing that came in. And presumably that's because that's what the dot did too, right? Somewhere between the upstream transform and the downstream transform, I have encapsulated the behavior of this dot. Okay, on to config. So I kind of went through this problem before. We've got things in the library. They've got their own config. They're all very happy sitting in the library, and their config matches what they're doing. But now you bring them together, and their configs need to have coherent values. So we needed a way to provide this coherence across. We could have done it with tests, right? The test could have come in here and said, okay, for all these elements that I've brought in here, let me make sure that I've put values in here that match with the values in here. But that can be very error prone, right? The test then has to know about all these things, all of these occurrences. We don't have a nice way to capture that and say, it's always the case that when this one has a value less than 5, this needs to be less than 10. We wanted to be able to capture that in the test bench, not really in the test itself. So that led us to this scheme of a tree of config structs. So the way that we do this is we build the entire configuration tree in a single randomization step from the top. So when a component is built, it's going to find its reference to the tree using the config DB. All right, so the first thing that happens in the build phase is we're going to build our tree. Right? All we're capturing now is what are we actually going to have in terms of configuration values. And from the layers up above, we can say what the coherent constraints are that will make these things work together. Then, of course, the build phase continues with building things under the TV top. So we'll build this guy here, and he will say, I've got a config, which I am now going to go find in the config DB, and I find this guy by name. Right, and so all of them have to do a similar thing. So we've got the configuration information here to know how to do the build phase, whether we're going to have this component have a driver or whether he's passive and he doesn't have a driver. All that information is right there. And then we'll connect up the configuration so it can proceed on. So this is not ideal. We'd really like to be able to put pieces down and automatically have everything they need there. Instead, we're left with kind of building two trees here, but we haven't really seen a better way to keep these together. So how do we do this? Kind of a short, high-level view of this. When the parent instances the child, he will go ahead and create the child, of course. And he will also do this config DB step where he's putting the config into the config DB. So when each component in their build phase is going to go check the config DB and see if their config is there. If it's not there, then that implies this must be a top level. So the top level will go off and have to randomize, and he will randomize whatever is in there. If he does find it, then he proceeds on. He's got his config. He now knows what to go do with it. One thing that's nice about this is we often have the need to do reconfiguration, particularly when we're talking about things on the line side. It's quite possible for someone to rip out an Ethernet port and plug something else in, and software goes through and tries to reconfigure everything and hopefully keep a lot of the other traffic still running. Well, we want to make sure that actually works. So we will often go through and do a re-randomization of a part of the tree. We'll sometimes do the whole tree, but it's more interesting to do part of it and see if the rest of the circuit still works. So if we need to do that, we can go through and set the rand mode to be 0 for all the branches other than the one we want to randomize, and then we go ahead and randomize the top tree, and we get all of the top level configs still apply, so we can't do anything in this re-randomization that is not coherent with the rest of the config, but it will randomize to the extent it can. Okay, the last thing here is the synchronization problem. So we're grabbing these pieces out of the library, want to make sure they play well together. Nobody goes racing on ahead and does things before other components are ready. So just looking at the needs aspect, we've really got our tests can always be shown as, we're going to start the test. We're going to go through multiple stages of reset. We tend to have actually 3 resets running around staggered. So the first reset comes in and, well, actually all the 3 resets usually get asserted, and then we start deasserting one of them. We deassert another one later and deassert the third one finally. But there could be 2 or 4 or whatever. There's multiple. And the same kind of thing happens in the initialization phase, where this is the initialization of the dot. So what we'll do is say, okay, in an initial phase, in an early initialization phase, we'll set that bit. Then we'll go off and do other things. Then in a later phase, we'll come back and say, did that actually complete? Have to pull for, did the memory thing complete? But that allows us to parallelize most of what's going on in the initialization. And then finally we get to the main point of the test, where we're sending in some packets, seeing what happens to them. We drain all those out. We do a final check to make sure that counter values are what we expect, etc. So that's the test here. All these other components have to feed into this, but they don't care about all of these things necessarily. If we take the reset IVC, what it's trying to do is initiate the assert of a reset, make sure that the reset is actually seen. If this was a software access, it might not be seen immediately. Initiate a deassert, and then make sure the deassert was seen. And then it's totally happy, right? Once that's done, it's completed what it needs to do. The sequences need to know about a starting point and an ending point. And sometimes there's a subsequence in there that's critical, and we need to make sure that we never interrupt it. That's pretty much all sequences care about as far as working together. So we just want to be able to tell them, here's when you start, here's when you end, and by the way, here's a piece that you better not ever break out of in the middle. And then finally, there's the rest of our components, the interface verification and the module verification. They really care about, I'm starting up, I'm in reset, I'm out of reset. For the most part, that's it. And that's why the recommendation's been to use the run phase, right? Because most of the time they're actually running. But we do need to worry about how we get this state information to them. And the scoreboard adds a little bit to that. It also cares about reset and out of reset, but it also has this concept of empty and not empty. All right, so what do we end up doing about that? So I showed you before we had this reset IVC. It's actually going to broadcast the information about what the resets do so that the components can call the appropriate tasks there. So all those components that just cared about, am I in reset, am I out of reset, they can get that information from the reset IVC. The stimulus, the test, and the scoreboard and the sequences, they use the runtime phasing that we have heard about. We've heard there's difficulties. We've heard you should limit your usage of it in various ways. And there's certainly some things that we have worked around there. So we'll try and share that. Okay, so we chose runtime phasing. We could have chosen here virtual sequences, right? So it's possible to say, I need to synchronize all the behavior of all the things that are in here. I'm just going to have a virtual sequence at the top that tells you to go do this, and you do this, and okay, now everybody stop, and okay, once you're both done, we'll go on and do the next layer, and so on. But the problem with that is that all of the information about what is in your test bench needs to be repeated in the virtual sequence, right? It needs to know about all the little things that every component can do. It's not the nirvana we're looking for, where we're just plugging things in and they know what to do most of the time. We can get that with the runtime phasing to a large extent. We can say, you know what to do in the main phase. When it gets there, you go ahead and do your thing, right? We don't need to tell you what to do most of the time. We do have some user-defined phases we're adding for the project-specific reset and config staging, right? So those are really for those multiple resets and multiple initializations that we had. We're not doing anything super complex with them, but we are adding those in, and so everything does run through these new phases. We definitely did not want to hard code any phases in the clients, right? It's got to be up to the integrator, the guy writing the test bench, to say exactly when things are going to respond. So if the component was in there saying, hey, I know I need to do things in the pre-shutdown phase, that's hard-coded in there, right? He's always going to act then, and I can't tell him, you know, what you thought you wanted to do in the pre-shutdown phase, I really want you to do in the shutdown phase. This is something we wanted to have. So we're avoiding hard-coding that by having everything be in configs. So the config is going to have the variable for the relevant phases. What's relevant for this particular component we've got here? So if he knows that he needs to do something in a pre-shutdown phase, we're going to have a config that says, this is what a pre-shutdown phase is to you. Typically it's going to be the regular pre-shutdown phase, but it could be passed in as something else completely. And each element's going to use phase started rather than the phase tasks, because as soon as you use the phase tasks, you have hard-coded in a particular task that things are going to happen in. So we can pass into this the phase that we want to compare against, and then we can call whatever task we want. Yeah?
Do you ever, in your components, jump from the main phase back into the reset phase?
We do, yes.
Your question, please.
So the question was, do we ever jump back from the main phase to the reset phase? So I don't think I really talked about jumping too much in here, but just to cover it quickly, we do jump back. We do say that the only time we're really interested in doing that is from the main phase back to the reset phase, and the only thing that really objects in the main phase is sequences. So we have built some things around sequences to make sure that they can jump back. Other than that, the components are going to get information from the reset IVC. If we do actually do a reset, they will see that the reset's there, and they'll go back into their reset state. So they should be happy, but we have had to work with the sequences. I touched a little bit on that in a couple of slides up, so I'll get back to a little bit more on that. So this is where we're showing the reset IVC sending out information from the analysis port. It comes into the agent that gets shared then with the driver and monitor. I've just shown some driver code here. The agent itself has some information here, taking the analysis port and deciding which state am I actually in. I haven't shown that. It's not very complex. I've tried to just show what the driver does with it. So what we see here is that the driver needs to do things in run phase. It's a forever loop, so in the run phase it's always running. That's what we want our driver to do, but we want it to do different things. If we are before the first reset, we might want it to drive unknowns, or we might want it to drive random data, or we might want to drive zeros. I mean, it's totally up to us what we want to do. But it's probably going to be different than how we want it to behave when it's in reset. So if we're actually getting a reset right then, we know that we have to drive our valid signal to be not valid, right? Because that's what the DUT's going to do. And once we get to after reset, now we're in the mode where we should be taking information from the sequencer and doing whatever the sequencer tells us to do. Right? We're not forcing valids to 0 all the time. We're just there. So we get in, we find our reset state, we find one of these tasks to do. These tasks go off and run whatever they're doing. Then we just wait for the reset state to change. Maybe the reset, once we get here, maybe the reset state never changes and we're off happily doing the sequencer stuff for the rest of the simulation. But if the reset state does change and we jump back to something else, say in reset, then we're going to disable the fork, killing our guy here, and move into driving and reset. Now this is code, and so what the user has to do is implement these things. I don't know why I called them something different. This should be these tasks here, right? The user is going to have to say what those tasks there actually are. What else do I want to say? Oh, so there's some variations here. You could put another line in here if you wanted your driver to respond a little bit late, to send a little bit of dribble information after the reset to test your DUT. You could put another task in here, but pretty much we're going to accomplish that by having the drivers be on a different reset domain. So if this was a driver representing something outside the reset domain that actually could be sending data after the DUT is back in reset, then we'll put him in his own reset domain, and we can have him continue to send because he thinks he's never in reset even though the DUT is, or we could subsequently put that other virtual domain in reset and have it send for a while, and then it stops as well. So we kind of get the control we need. Who controls all this phasing here? So I've shown the primary phases that we use. I mean, there's others, but they didn't really fit on the chart very nicely. Who determines how long pre-reset lasts? That's really the test, right? So you might say, I really want to make sure that things don't do anything before I put a reset in there, or they don't behave badly when I have my drivers sending unknowns, and you could extend this out. Or you might say, I don't care about testing that anymore, I'm just going to immediately go and do reset, and that's fine too. As far as how long the reset is, I could have put something in here for the test as well. Often we'll have things for the MVC because each DUT kind of has a spec for how long it needs reset to be held. And by using this mechanism with the objections, each guy determining how long he wants to be, we're automatically getting the longest one of those. So whoever says I need the reset for the longest, that's how long the reset's going to be. And it's kind of nice it automatically happens. Post-reset is often determined by some kind of control status register sequence that is going through and removing resets because that's the way we do resets. We typically have them be sourced from a register. So to deassert, you actually have to do that. Your implementation may vary, but that's what we do there. And then configuration is all based on control status register stuff. The main is based on perhaps a test saying I want to run for 50 microseconds, and the sequences just go until 50 microseconds is up. Or it could be the sequence itself needs to accomplish a certain thing, and when it finishes, then we're done. And then we go into shutdown. That's determined by the scoreboard that's in the MVC, because we need to make sure that everybody's out of here. And finally, the post-shutdown is where we do our final checking, reading, counters, and things like that. And so that would be back on the sequence again. So you'll see that most of the determination here is really in the sequences, right? These are really saying how long most of these phases are. We get some voting here from the MVC to say, I'd like the reset to be a certain length, or I'm still busy with getting rid of data. And the test can jump in at any point, but the places we really see it is pre-reset and perhaps saying how long we want the sequences to live for. Okay, so I mentioned we'd need some phasing workarounds, and I got 2 minutes to do it, so let's see how I do. So one of the problems that people have mentioned with phasing. One of them is that sequences are not phase aware, and you saw in the previous chart that sequences are highly involved with what we're doing here with our with our phasing. So what we can do there is we can use the sequencer, which is phase aware, and have each sequence point to that and get information from it, which is exactly what we do. What that means is that we can't really have virtual sequences working on sequencers in different phase domains because there'd be no good way to get the information from the various sequencers down to it and know which was working where. That's a trade-off we can make, right? We don't really have a need for doing that too often. So we just have the sequencer currently feeding information about phases down to its sequences, and the sequence, well, the sequencer basically triggers an event, and the sequences go look at that event. Another big problem is the process control that's in phasing. It's really a brute force right now. So when a phase ends, it basically goes out and kills everything that's there. And sequences aren't very happy with being killed like that. So we have actually had to build a decent amount of infrastructure code around sequences to avoid that. It ultimately comes down to the sequences need to recognize that a phase is going to end. Maybe it's their end phase that's been configured, so that's when they're supposed to end anyway, or maybe a jump's occurred. But in either case, we need to tell them to do that before it actually happens, and then they clean themselves up and kill themselves, and then we're allowed to move on. Another problem is this jump action is immediate. There's no request to get ready, and many components can't handle that. So we've added another user phase to allow for ready to restart. So there's a phase where components can go through and say, oh, we're in that phase, that means we're about to do a jump, I better clean up, and when I'm done with that, I'll tell them I'm done. One reason this all works is because we're writing all our code, right? So we're not, we've kind of lost the UVM advantage of we're able to share from anybody because we're relying on a number of things here that are just entirely within our own code. So when we get other code, potentially in the future, we have to work out some kind of layer around it to make it work in here, and that's going to be difficult too. So this kind of works for us. It allows us to get all the phasing that we want, but it's not ideal because we really would have a hard time bringing in other VIP. Okay, so my summary slide, and we're out of time, it's basically the same things I said before. We needed this, to make this library element-based creation, we really needed to have a flexible structure of the verification components, a checking scheme that we could modify, a way to get the configuration coherency, and a way to synchronize all these library elements. And what we see here is what we've done so far.